setup of decoder-only models, what we do, we feed some prefix, some prompts to LLM. We compute the next token. We append this token to the input sequence. We get a slightly larger sequence, and then we repeat the process. So that requires a lot of computation. So instead of recomputing everything, some values are cached. Keys and values on each layer, on each transformer layer, are cached, so we don't need to recalculate them. In that case, we don't need to recalculate all the queries. We only need to calculate the last query in order to attend to already stored keys and values, and that's how all decoder style large language models work. But there is a drawback. It requires a lot of memory to store keys and values, especially for longer context. So the scope of our work is to use block floating format that is supported by our device to store keys and values in some low bit format, while we don't worry that much about queries, because we only calculate one query per each token, per each pass of per each step of generation. So in this particular work, it's only about keys, so we even don't talk about values here. And importantly, it's all about activation. So it's not about the weights of the model. Weights could be already quantized, and that's still the result is still applied to the activations. So what is block quantization? So block floating point format is basically just a block of matrices of some integers with a shared scaling factor. So it's very similar to a floating point format, but it doesn't use, so the matrice is not significant digits after the decimal point. It's a set of integers, so that allows to use one scaling factor for different numbers of different order of magnitudes. But the smaller numbers closer to 0 will have less significant digits. So blocks should be aligned along the rows or columns of the matrix, depending on how this matrix will be used. So the matrix will be used for the first matrix multiplication. So in order to compute it efficiently in the core of the device, the whole block should be multiplied by the whole block. So that dictates the direction along which the blocks should be aligned. The blocks are, so different block sizes are supported by the device, but typically for large language models with a few billion parameters, the head dimension is larger than blocks, so we have a few blocks per head. And as I said, few numbers share the same scaling factor. Scaling factor is usually a power of 2. It's as the scale is determined by the largest number, the smaller number suffers from less precision because they have less significant bits. And authors of different papers of smooth quant, of KV quant, notice that there's empirical evidence of outliers in different channels and LMs, particularly in keys. And these outliers are persistent along different tokens. So, but given our block floating point format, keys should be quantized along the channel dimension, because this dimension will be used in order to get a matrix multiplication with queries in order to get a score, attention score. So that means that we will mix large and small values together in one block, and as I said earlier, it decreases our quantization precision. So ideally, we would like to rearrange keys in, so the large by absolute values get in one block, the smaller into another block, but we cannot do it in runtime. It's infeasible. But what we can do, so keys are just a result of multiplication of projection matrix WK with the corresponding input. There could be bias, but I think in most popular configuration models, same Llama or any other model I can think about, the bias is off by default in the most popular configuration, in pre-trained ones. So yeah, keys are just WK multiplied by input. So instead of grouping keys together, we can group rows of WK together, and that could be done in compiled time. So we load the the neural network on our memory and device, we rearrange the rows, and only after that we can start inference. So, and that leads to our algorithm, which is a very simple, very naive algorithm. So we calculate the norms of rows of WK. These norms can be L1 or L2 norm. We sort matrix WK according to its norms. We do the same transformation with matrix WQ because keys and Qs are only used together. In infinite precision scenario, it doesn't change anything. It's absolutely the same numerically, but in our finite precision blocks, it helps us to bring keys of large amplitude of these outlier channels together in one block, and some smaller channels in another block. There is some catch. So a lot of LLMs, including Llama, use rotary embeddings. So rotary embeddings, they basically entangle channels pairwise. So for each channel, there is a corresponding channel. And because this matrix, so rotary embeddings is basically a sparse orthogonal matrix, and actual calculation of rotary embeddings is not a matrix multiplication. This kind of SIMD operation, but for each channel, we need corresponding complementary channel and its sign. So it's implemented slightly differently on actual implementation of Hugging Face and Llama. So instead of pairing even and odd channels together, channels from first part and second part paired together, but it doesn't change the picture overall. But what's important is by default, this order is we don't need to remember it because it's very specific. It's easy to compute. In our case, if we reshuffle this order of channels, we need to remember the order of corresponding complementary channels. So we need some additional memory for it. But again, because this is all done offline, it's all applies to the order of rows WK. We only remember it's once per each layer. So we don't the memory required for this to remember this order, it doesn't grow with the context length, it doesn't grow with the sequence. So yeah, we also need to store keys before applying rotary embeddings, and then apply them on flight. But in memory bound scenario, it still allows us to basically to store keys more efficiently. And yeah, so and I have some results for Llama 2 7B perplexity on Wikitext2 dataset. We used run CLM script from Hugging Face, so it's different from Elite harness, which is widely used. So dataset is partitioned differently, so the numbers are different, but we can still see the comparative results. So that's a baseline for FP16, and for block format of block size 128, where keys are stored in BFP12, meaning 4 bits per mantissa and 8 bits for exponent, and queries stored on 8 bit for mantissa, we can see that our algorithm does nothing. That's because the head size of Llama 2 is 128. So if the block size is 128, we sort the channels, but they're still within the same block, and it doesn't impact anything. But with block size of half or quarter of head size, we improve perplexity significantly and approach to the original one with the block size of 32, while quantizing keys from FP16 to 4 bits per key and one additional exponent per every 32 elements. So yeah, so just to conclude, so the scope of this work is that key counts should be kept in low bit format, and we can use block floating point for it. It's fit for purpose, but keys have outliers, and simple reshuffling of weights of matrix WK to group the channels together helps to improve quantization precision. Yeah, that's all. Thank you.
First line, like block 14.16.
Yeah.
Is that 8?
Oh yeah. So yeah, I told you, but maybe not. I'm not loud enough. So BFP 16 means it's our internal disambiguation of a format. So BFP 16 means 8 bit per exponent, which is 1 per every 128, 64, 32 bits, and 8 bit for each element. And so queries are kept in a quite high precision, but again, we don't store them in cache, so we can allow it. And keys stored 4 bit per element and 8 bit for exponent. 4 bit per element and 8 bit for shared exponent. Yeah, so we keep 8 bits per exponent because kind of that corresponds to FP16 range, and otherwise, if we have low exponent, then we have some additional problems that simply some high or low values can be out of range and basically turn to infinity. So we try to keep a similar dynamic range, but the precision is much lower. Mm-hmm. Your algorithm works. How do you do that? So basically, again, we anyway we so these cosine and sinus, you're right. They kind of we don't if we calculate them all, it will be probably expensive to do. But in a common rotary embedding implementation, this cosine and sine, the parameters are not trainable; they're fixed. So they're the same for each layer. We need additional memory to store them recalculated, but and this memory grows with context, but it's only once per kind of we don't so for example, if we have 32 layers in our model, it's the same for every layer, so we only store it once, and it's additional record which grows with context, but it grows significantly slower than key cache if we have a large number of layers. So we I haven't run this particular algorithm on a very kind of large models, so I only run on something that fits on one GPU. So Llama 2, 7B, some OTP, and GPT-2. But generally, if we talk about the format in general, then we have it tested for weight quantization in a lot of popular models up to 70 billion parameters, and it works fine with them. So yeah. Thank you.
Our next speaker is virtual. Songhan.
Hello. Let me share my slides. Can you hear me?
Contributions on decompression technique, mostly it's powerful artificial intelligence programs, then more efficient code on mobile devices. He received the NSF Career Award for efficient algorithms and hardware for distributed machine learning. AI is free to watch the future of AI award and the Sloan Research Fellowship. His research in efficient AI computing has witnessed successful commercialization and influenced the industry. He was the co-founder of DeFi, now part of AMD, and co-founder of OmiML, now part of NVIDIA. He also developed the efficient ML.ai course to disseminate efficient infrastructure.
You can start, Professor. Can you hear us?
Okay, great. Yes, I can hear you. I mean, somehow I cannot find the Teams. Let's see. My Teams has a little bit of problem here. I was able to share just a moment ago. Okay, there we go. Let me share the screen. Okay, there we go. Now you should be able to see my slides moving.
Yes.
Okay, great. Great. Hello, everyone. Glad to present efficient multimodal large language models. So recently, there is a growing demand for multimodalities, not only to deal with language, but also to deal with vision. So how do we efficiently combine visual model and also the language model? First, to build efficient extractor for the features for both the vision and also the language, and how to efficiently combine them together, and how to efficiently deploy them both on the edge and also on the cloud. That's a full stack design problem from both the algorithm side and also the system side, from both the demand of computing and also the supply of computing. So in this talk, I will talk about efficient feature extractors for visual models with efficient VIT, and also efficient feature extractor for both large resolution image and also long context language. Both are computationally challenging for both long context and also large resolution. I will also talk about how to efficiently combine visual and language with the VLA visual language model, together with how to efficiently quantize the multimodal large language models with AWQ, and also how to build an efficient inference engine so that we can deploy such multimodal large language model on edge device such as Jetson or Nano. Concluded by how to efficiently generate these models using condition-aware neural network. So let's get started. So there's a huge demand for efficient computing, and software is getting a large proportion of the total design cost. So in this context, model compression plays a critical role to bridge the gap between the supply of computing and also the demand of computing. I've been working in this direction for roughly a decade since my PhD, and also after joining MIT, we've been working on a lot of projects in this direction. So prior work, including deep compression and EIE, which was the best paper award in iClear 2016, it's already 8 years ago, introducing pruning and quantization now is the standard practice in industry for compressing neural nets. And in the context of large language models, these methods are getting increasingly more important, given these models are 3 orders of magnitude larger than like ResNet 50. And I introduced the first accelerator to support this weight sparsity, which is the EIE, Efficient Inference Engine, on compressed deep neural nets, which was one of the top 5 most cited papers in 50 years of the ISCA conference from 53 to 23. And pruning and sparsity has increased attention since 2015, 2016. It's been a growing trend. So these days, we've been working on algorithm system co-design for accelerated AI computing, both tiny model and large model, which I'm going to motivate with starting with tiny model and spend most of the time of this talk introducing efficient large models, dense to sparse, full precision quantization, inference to training, discriminative to generative, which I'm going to cover both single modality to multimodality. One of my PhD students, Henry Wang, he worked a little bit on quantum systems as well, but it's not the scope of this talk. So a little bit of retrospect of TinyML, where we've been able to fit visual models in tiny devices with only 30 kilobytes of SRAM throughout the years from 19 to 20 to 21. Every year we've been shrinking the models, the measured memory consumption by half. So we have a couple of demos here, including on-device inference, running inference of visual models locally on such microcontrollers that has only 632 actually kilobyte of SRAM for a visual wake word and only 256 kilobyte for person detection. For example, detecting the people sitting far away, or even detecting faces and masks. We've been also enabled this on-device training, not only inference, but also training locally on microcontrollers. Here we have only 512 kilobytes of SRAM available and 2 megabytes of flash available here. You can see there are 2 buttons, the red for person and the green for no person. Initially, during the random test, it cannot, random initialization, it cannot recognize person versus no person. But later we can push the button and use on-device training technique. We publish in EMC2'24, including sparse update. No need to update all the layers, all the tensors. Quantization aware training. Quantization aware scaling, so that we can make inter-8 training still converge. And finally, tiny training engine to implement the algorithm advancements into measure the speed up. So both inference and training, I categorize them as Edge AI 1.0. So we train a specific model for each task, like person detection, like autonomous driving or manufacturing translation. Those are task-specific models. When you have outliers, especially for smart manufacturing, you want to detect those abnormal scenarios. There is a shortage of corner cases or outlier scenario, the autonomous driving scenario. So we need different model, different data to train on different tasks, a lack of negative samples for training, and limited generalization, failure on corner cases. So Edge AI 2.0 will exploit large language models to improve the generalization capability with more world knowledge. Using only one model, perform multiple tasks. The world knowledge stored in large language model can help with the reasoning capability and having those instruction following proficiency for landmark recognition, driving assist, patient monitoring, smart manufacturing. I'm going to demo a few cases later using just one single model called VLA, the visual language model. So the first half of the talk, I'm going to talk about how to pre-train VLA and how to compress VLA from a large one to a smaller one, and also how to deploy VLA with TinyChat. So VLA, visual language model on the edge. So the goal is to train a multimodal large language model to enhance the visual reasoning by language model, since we learn more world knowledge in the textbooks, in the text, than the images. So enable in-context learning and reasoning across multiple images. So here we augment the large language model's input with both the text token and visual token with interleaved visual and text token. For example, here is an image of panda passes through a VIT projector, projected to the visual token and followed by a text token, followed by visual token and text token. Different from prior work here, using interleaved image text rather than just image text pair can enable this in-context learning capability. And here is a demo. We can actually deploy VLA, a JSON ORIN. For example, here, what is unusual about this image and its safety concerns, I can tell you is hanging a rope attached to a wind turbine blade. There is risk of falling with injury dangerous. We can also ask the same model, how many cars are jacked up. We never train a car detector, but it can tell 2 cars. And actually, it can reason about what does it mean to enter the car, and what is the brand of the car. Can tell it's a Jeep, although we never train a car brand classifier, or even an aerial view can tell how to describe the traffic with a different viewing angle. And also the corner case for driving. For example, a couple of deers are crossing the street. You can precisely tell the special condition, and you can ask, should the driver honk at the animals and why? It's a corner case, but it can combine the word knowledge stored in large language model to tell you it's not recommended to honk. It can startle the deers. It's dangerous. So that's the magic of VLA visual language model on edge device. So VLA also has this in-context learning and multi-image reasoning capability thanks to the interleaved image text pre-training. For example, we give some context, logo, search engine logo, operating system, Apple's logo, iPhone, iMac, and give the NVIDIA logo, can tell it's famous for GPUs. Also, we can give several landmarks and can tell this is the home to the greatest pizza. Although we have never told the model to, the task is to predict the food associated with the city, but it can automatically deduct the task. This is in-context learning. Or even this famous example, we have 2 Magna beers, and then we can ask, given these 2 images, how much should I pay for the beer on the table according to the picture on the menu? We can enable this visual chain of thought, let us think step by step, and then it can tell the beer is Magna, recognize OCR is a Magna, and then it can associate Magna's price, $6 here, and then do the math. 6 times 2 is $12, reasoning across multiple images. Can also ask to tell the implication of temperature based on these 2 images. So it requires reasoning across multiple images, and it can tell you this is Arctic ice cover in 1984 and 2012. Significantly decreased. The ice cover is significantly decreased, which is a result of climate change, warmer temperatures. So very precise reasoning across multiple images. Here are some other examples of multi-image in-context learning example. I'm going to demonstrate a few other scenarios for explainable driving, just using exactly the same model without task-specific training. Should you honk? Not appropriate to honk, implied and disrespectful. In an in-car driving scenario, you can tell if the driver is distracted. Is the driver on the phone? How many people are there in the car? Where is the passenger sitting? There's no particular fine-tuning, but very good generalization capability. Abnormal detection. Do the facilities look normal and looks in good condition, well maintained? Versus in the patient, the same model can tell she's in a critical condition, ventilator, she's asleep. And this is an interesting case. Will the practice cause pain to the patient in the image? Actually, this is a dummy person, and can tell it's a simulation and not a real patient. Does not cause pain since it's a mannequin, not a living person, which is very good word knowledge. They can also reason across videos. So like we can ask how many chip bags are packed to 5 input images sampled at 2 frames per second. How long does it take? I can do some math and tell you take 1.5 seconds to pick up the chip bag. Some other examples is the building in healthy condition. So we never train a specific healthy condition predictor in this case, but the same model, VLA model can tell visible cracks and chips damaged or worn. So very good for edge AI scenario, just have the same model to do many different tasks. But the next question is how to deploy such visual language models, and which is the bottleneck? And actually, the visual encoder is not the bottleneck, but the large language model is the bottleneck. So we'll talk about LM compression techniques by smoothquant and AWQ. So quantization can enable more efficient inference, but the outlier problem, this paper we published back in 2022, is finding there's a huge amount of outliers in the activation of the language models, and they persist in fixed amount of channels. So the idea is that rather than using mixed precision, which is GPU unfriendly, we want to achieve measured speed up. We actually have another approach, which is to use a mathematically equivalent transformation to smooth away those outliers. So this is activation, lots of outliers, weight pretty smooth. What we do is that we can multiply this channel by 0.1 and multiply the corresponding weight channel by 10. So the result is still the same, since 0.1 times 10 equal to 1 by 1. As a result, we can smooth away the outliers in the activations and then make the weight a little bit more rough, but it's still very easy to quantize. So we effectively migrated the quantization difficulty from the activation to the weight. This is a real world, this is an example illustrating how it works. So this is a previous activation times the weight. There's an outlier channel on the second channel. And we can use a smoothing factor 1413, which is a square root of 16 times 1, actually. And here we can smooth it such that the 16 and 8, for example, here 16 times 1 equal to 4 times 4. Okay, and here 8 times 1 equal to 2 times 4. So we effectively get the same result, but we can smooth away the outliers in the activation channel. Okay, and the smoothing factor can be, it's just in the diagonal direction, which can be safely merged into the activation function into the previous layer in the epilogue of the CUDA kernel without introducing any overhead. So smoothquant achieved a good measured speed up and also the measured memory reduction. So actually using half of the number of GPUs, we can be even faster. Okay, previously using 8 GPUs served with IP16, now only 4 GPUs, and it's even faster with half the GPU memory with the measured results. And the accuracy is very well maintained across different models. We even evaluated with NVIDIA's Megatron Turing NLG 530 billion parameter model, reducing the node from 2 nodes to only 1 node. The latency stays pretty much the same while having the GPU memory with the same accuracy. Okay, so we want to switch gear to talk about single batch serving. Okay, so previously we were talking about the large batch serving, which is actually a challenging problem. But on-device serving suffer from the memory bandwidth issue. We are here in the roofline model rather than here. It's highly memory bounded, so therefore we want to reduce the weight. So we developed AWQ to appear at ML6 this year for on-device LLM to deploy a large language model on the edge like JSON Orin or AIPC, like in this demo. We are asking the AWQ quantized model to sort an array. The challenge is that they are weight memory bounded at low batch. It cannot fit, make the ALUs idle. So we use a 4-bit weight FP16 activation, FP16 arithmetic. Different from conventional wisdom, we advocate for activation awareness to preserve the salient weight channel by scaling according to the activation's magnitude, rather than scaling the weight channel by the weight's magnitude. So it works quite well. This is a key technique behind NVIDIA's chat with RTX, where you have if you have a GPU laptop, you can run Llama 13B or Llama 7B or Mistral 7B on this laptop. And here is the measured speed up compared with FP16 using AWQ measured on Orin. Can run more than 30 tokens per second for the 7 billion parameter model. So how does it work? When we are doing the quantization, round to nearest will drastically degrade the perplexity. even using the group quantization method. And we find about 1% of the channel are very critical. Okay, if you keep them as floating point, you can drastically improve the perplexity. However, we don't want to naively select those channels. And how do we select those salient channels? And do we really need FP16? Can we be smart and get rid of this mixed precision? Okay, just using fixed integer to represent all the weight activations, including all the weights, including the outliers. So how do we select the salient channels? So during pruning, when we are pruning the channel, we look at the channel. If it is large, then we keep it. But here we do not look at the weights, but we look at the activations. If the activation channel is large, then we should protect the weight. This corresponds to the outlier observation in smooth quant, where these outlier channels are very crucial. We should protect them. So how should we protect them? So one way is actually using this using this mixed precision, but the FP16 is not hardware friendly and we require complicated kernel writing. And we can use a smarter way to actually fuse the scaling factor to the previous operation by expanding or enlarging the channel whose activation is large. Okay. So in this mathematically equivalent transformation is very similar to smooth quant mathematically wise. So we can enlarge the weights whose corresponding activation is large. If you multiply by 2, effectively you're actually giving it one more bit. For example, if it is 0.499, previously it will be clamped to 0, but after quantization, after scaling it by twice, it will be quantized to 1. So effectively, you can distinguish 0 and 1. So you added one more bit for that channel. So that's why scaling up the channel can protect it. So we get rid of the mixed precision and make it very easy to implement and achieve measured speed up. It also has quite good generalization capability since this simple scaling-based method doesn't require any backpropagation, so like GPTQ. So for example, when we are reducing the calibration sequences, even like 32, the perplexity of AWQ is very well maintained rather than exploding. And also when you switch from one data set to another data set, methods like GPTQ require the calibration and fine-tuning on top of that data set, resulting in a big gap if the evaluation and calibration data set are not the same. But here using AWQ, you can very well maintain the accuracy, despite that the evaluation data set and the calibration data set are quite different. So AWQ is very robust to calibration set distribution. So this is the accuracy about the quantization approach with RTN, GPTQ, and AWQ for different group size, for different precision in 3, in 4, is demonstrating consistent advantage. It also works quite well for multi-model large language model. Since this is the central topic of today's talk, we feel it's very crucial to maintain the generalization capability, not only for language model, but also for visual language model. So thanks to AWQ, just require simple scaling without fine-tuning, without any back propagation. It doesn't overfit. So it generalizes quite well to visual language model. Like previously, RTN model says airplanes flying in the sky. AWQ says two toy airplanes sit on a grass field. RTN method says a man is holding a baby elephant in the arms. AWQ says it's posing with an elephant. So big improvement under the 4-bit quantization. For example, here is the quantization result of Open Flamingo for captioning. So the Coco Sizer score here is a lot better compared with these two different baseline models. And here we combined AWQ for Villa to do the co-design and quantize the Vela 7B and also Vela 13B with the AWQ model. Compare the FP16 in 4 model, the average accuracy is very well maintained for 7B model and also the 13B Vela model. And SmoothQuant and AWQ are both available in NVIDIA TensorRT LLM. So TensorRT LLM is the state-of-the-art large language model inference framework from NVIDIA. It incorporated a lot of advanced techniques here, MHA, MQA, GQA, infinite batching, page attention, etc. And quantization methods, SmoothQuant and AWQ is natively available over there. And using AWQ, actually, you can deploy a 180 billion parameter model on a single H200 GPU. Despite that, the memory here is only 141 gigabyte. Thanks to AWQ, can compress the model to only 90 gigabyte. Then it can fit. Okay, so it also has been widely used by the community with almost a million AWQ quantized models has almost a million downloads from Hugging Face. So no matter if you have large language model or visual language model and want to try to deploy it efficiently, AWQ is a very good approach. Okay, thirdly, let's talk about inference engine. So we'll present the TinyChat LLM inference engine on the edge. So we want to deploy an inference engine for research, Pythonic, lightweight, efficient, easy to use, and also efficient. So we want to get the best of both worlds for research purpose. Okay, so we built this TinyChat, a lightweight large language model inference library, which achieves up to 1.5 faster runtime compared with systems specialized for this model. It's fully PyTorch based, but it has very good performance compared with running on different benchmarks, including these coding benchmarks. We also seamlessly support visual language model with the TinyChat engine. So this is the Vela model measured on different GPU platforms with A100 GPU, 4090 consumer GPU, or even the Orin driving GPU. Comparing the FP16, we can roughly triple the performance, the throughput measured in tokens per second, more than triple in this case. And also for the Vela 13 model, 4090 ran out of memory with FP16, but using the AWQ with TinyChat, we can run almost 100 tokens per second. So here is showing the demo running the Vela model quantized by AWQ served with TinyChat. Oh, so this one is only the large language model, So this one was the visual language model, which we just saw, combining the Vela with AWQ plus the TinyChat. And also the TinyChat support different platforms, including the GPU laptop and also the CPU laptop. On the right-hand side is running purely on the CPU of a MacBook, which is running at a pretty high speed. We even deployed it on a Jetson Orin Nano, which has only about 6 gigabyte of available memory, excluding the operating system. So here we enable the efficient deployment of a 7 billion parameter large language model with AWQ quantization and also TinyChat engines deployment. And in the back, you can see this is actually a small Jetson Orin Nano in the back. We hope such techniques can enable private on-device deployment of large language models. And recently, we also released the Vela 2.7B, which is also deployable on a Jetson Orin Nano. We also built a web UI to show the demo. You can feel free to try it out at vela.hanlab.ai. It's a pure open source project, including both the training code and also the quantization code with AWQ and the deployment code with the tiny chat. You can also deploy it on your laptop for this visual language model very easily. No matter if you have a MacBook or you have a GPU laptop, etc. Okay, so a short summary here. So Edge AI requires full stack optimization. So VLA is on the neural network, the application side, which drives the demand of computing. We use interleaved image text to train the visual language model to enable this multi-image reasoning and in-context learning capability. Then we can compress that before deployment using the AWQ quantization, and finally building better systems, which is the supply of computing, which is the tiny chat inference library to serve the visual language model. Okay, so that's the first chapter of the talk. Now I'm going to switch gear to the second chapter to enable long context learning and also the large resolution learning. Both are very computationally heavy and also introduce a lot of computing overhead and challenge. So we want to solve these problems using streaming LLM to generate long text, and also using long LoRa to fine-tune the model to increase the context length. And then I'm going to introduce large resolution scenario, introducing distribution with a new parallelization dimension across the patch dimension, so that we can enable distributed inference for high resolution image generation, followed by efficient VIT, which is an efficient large resolution visual encoder, and also the CAN, the condition aware network, which is an efficient method to inject the condition into the image generators. So let's first start with streaming LLM to enable long conversations in non-stop streaming applications. So without streaming LLM, after a while, the model performance breaks, and then you run out of memory. But with streaming LLM, you can enable these multi-round dialogues where the long and non-stop interactions are needed with the constant memory. So the challenge here is that the KV cache grows linearly, and extensive memory consumption is needed when the conversation gets long, and the perplexity will explode after the sequence length exceed this threshold. So without streaming LLM, the model collapses as the conversation gets long and then run out of memory. But streaming LLM, the non-stop conversation continues. So how does it work? So conventionally, the dense attention KV cache grows linearly with the sequence length. The perplexity will explode after exceeding the maxed context length, like Llama 2 7B is 4K, Llama 3 is like 8K. We can we try the window attention, which use constant KV cache, but actually the perplexity will explode after the sequence length exceed the KV cache size when the first token is evicted. As soon as the first token is evicted, the model collapses. And streaming LLM finds a very simple solution. So just use always pin the first token in the KV cache. Always keep the first token in the KV cache, and for the rest of the token using a sliding window manner. And then it can effectively stabilize the perplexity. The perplexity no longer explode, and also the KV cache size is constant. It's very helpful for conversation where you just interact with the nearest contents, but you can keep the conversation going without breaking it. Actually, we find, we call this phenomenon called attention sink for this first token. The first token is always very heavily attended in large language model. We call it attention sink. Like in this sentence, he is a very famous researcher in the computer architecture area and has published many, and we generate papers. And back in 21, when we published this Spartan paper, Spartan for sparse attention to prune the tokens, we found this interesting phenomenon where the first token is very heavily attended, but we didn't find a solution. Also, in this case, Du Fu was a great poet of the Tang Dynasty, etc. We can gradually prune a lot of tokens using the Spartan approach, sparse attention approach, but we can never prune away this Du, which is the last name, which is quite interesting. His first name can be pruned, but the last name can never be pruned. Later, we did some in-depth analysis last summer with my student Guangxuan, and we find the first token is very crucial. It's not semantic due to the semantic, but it's due to the position. Okay, due to it's the first token that can be attended by all the later tokens. Okay, and why the attention sink exists? Because the softmax makes sure the attention score need to sum up to 1 for the row. Okay, for all the contextual tokens. Even if some of the tokens are not relevant, you don't want to attend to it, but you still need to dump it somewhere so that it can sum up to 1. Okay, and we call that token to be attention sink. And why the first token is attention sink? Because that's globally visible. Second one can find it, the third one can see it, fifth one can see it, etc. So what should we do with attention sink? It's very simple. We just always keep the attention sink tokens in the KV cache. Okay, so it's a very general phenomenon beyond the layer 1. The model very heavily attend to the initial token. And some of them has this lambda pattern where the initial token is very crucial and the recent tokens are very heavily attended. So that opens a lot of room for improvement. So after this paper is published, people find this attention sink phenomenon actually exists in many different models, including the visual language models. And also not only the autoregressive models, but also models like BERT. So the recipe is always keep the attention sink tokens in the yellow part in the KV cache. In practice, 4 tokens is a good sweet spot. Another trick is that we should use the positions in the KV cache instead of the positions in the original text in the positional encoding. And in the bottom, we can see that the dense attention will fail beyond the pre-training window size. Okay, and this windowed attention in orange will fail after the input exceeds the cache size when the first token is evicted. And streaming LLM demonstrates no perplexity explosion. So we have tested up to 4 million tokens. And MLC actually integrated that and deployed on iPhone. And streaming LLM on iPhone is shown in the demo on the right. And compared with sliding window with no recomputation, streaming LLM actually demonstrated a very good speed up. And actually, the more you generate, the more you save. And streaming LLM is also available in NVIDIA TensorRT LLM. So if you're interested in playing with streaming LLM, feel free to go to the TensorRT LLM and find the off-the-shelf implementation for Llama 2 7B with streaming LLM. Okay, so streaming LLM enable long generation, but how do we enable long context? That requires fine-tuning, but fine-tuning is pretty expensive for the attention stage, for the attention layers, since the computation is quadratic. So in this EMC2'24, we have this oral paper called Long LoRa, efficient fine-tuning for long context large language model. So we can, rather than use a mathematical equal approach, here we use shifted sparse attention for the computation of the attention layer. So we only let the tokens within each group attend to all the tokens within the group. But how do we enable adjacent groups to communicate? So here we use a very smart approach, use the shift, okay, similar to the transformer approach. So here we shift half of the heads by 2, so that half of the heads can attend to the second group. Okay, so this is just one layer. You expanded between group 1 and group 2. So with 2 such layers, you can extend it by 4, etc. So all the way, when we get deeper, all the groups can attend to each other. So this reduces the complexity from O(n) squared to O(n) times m. Here m equal to 4. And that can reduce the perplexity compared with simple LoRa-based approach, which basically LoRa doesn't work quite well for long complex fine-tuning. The capacity is simply not enough, and we find fine-tuning the embedding and also the normalization layer is very crucial. And here, the long LoRa can match the perplexity of full fine-tuning, but a lot faster than the full fine-tuning. Basically, full fine-tuning is basically running out of memory in this case. And it's already using the flash attention for the base case of full fine-tuning. And here in the passkey retrieval task, originally Llama has 4K context length. We can effectively push it to 32K using just one single 8-card A100 machine. We can also extend it beyond that a little bit by using the extended position interpolation. Okay, so long LoRa and streaming LRM provide efficient fine-tuning techniques to extend the context length and also to generate long text. So how do we deal with the second problem, which is large resolution? So for the last 15 minutes, I'm going to cover district fusion, efficient VIT, and also condition-aware network. So after SORA, people want to generate high-resolution image and videos, but the computation is huge and the latency is pretty slow. But how do we quickly iterate by exploiting more GPUs? So the goal is to enable distributed parallel inference, exploiting multiple GPUs to accelerate high-resolution diffusion models. The naive method just distribute the activation, like here, distribute the activation in 4 parts to 4 GPUs by splitting the images into patches. Here we have 4 patches. However, we find such naive parallelization lead to strong artifact with duplicated object. 4 GPUs generated 4 figures due to the lack of patch interaction. Although it's about 3.9 times faster, the artifact is bad, and it's due to the lack of patch interaction and communication. Our approach called district fusion communicate the patches and reduce the activations from the previous patch to hide this communication overhead, this networking latency. Using the intuition that since the diffusion model require multiple steps and different steps feature map look similar, and then we can use the old step, the stale stack, to communicate with the neighboring GPUs. As a result, using 4 GPUs, we can achieve about 3x speedup. If we can better write the system to fully overlap the communication with computation, we can achieve even better speedup. And here we can effectively get rid of this overhead, this artifact of duplication. Okay, so this is the generation. Another critical part is understanding and to try to deal with high resolution image encoding. So to apply transformer to high resolution image is very difficult. It's very crucial because otherwise it will miss certain objects. Like you can completely miss this motorcyclist. So you have very low. If you have low resolution, the MOU, the accuracy is pretty low. But if you have high resolution, actually using the transformer, the Gmax, the computation grows much faster compared with using CNN. So transformer is actually not friendly for this large resolution scenario where the computation cost grows quadratically as the input resolution increases. So what we do is a new backbone called efficient VIT that can accelerate the model by more than an order of magnitude. Here, 21 frames per second compared with 1.6 with even better accuracy. And this is measured on AGX Orin with tensor RT IP16 batch size of 1 on the segmentation task on cityscapes. So how did efficient VIT work? So it first used linear computation, okay, linear computational complexity using linear attention, and with global receptive field using only hardware or friendly primitives and enable multi-scale learning. So to keep it simple, we replace the softmax attention with the linear attention, basically using the associative property of matmul. We can calculate the KV first and then Q. Simply using this ReLU linear attention, although it reduced the cost for ON compared to ON square, the critical missing part is it misses this local feature extraction capability. Okay, so we need to come up with a smarter idea to compensate for this sharp local feature extraction capability, like here for softmax attention. For linear attention, you don't have such good local feature extraction capability. And using that naively, using the linear attention naively, we will have a huge accuracy gap. So what we do here is actually adding the local feature extraction capability using a simple depth-wise conv, which is actually a very smart design of the depth-wise conv, which can be we can specialize that for local feature extraction and specialize the linear attention for global feature extraction. So just like hardware specialization, here we are also exploiting the specialization idea. And as a result, we can actually get even higher accuracy using the specialization. Okay, convolution for local feature extraction and linear attention for global feature extraction. And here on different platforms, including Snapdragon CPU, Orin mobile GPU, and A100 cloud GPU, we can achieve 1.7 to 5.8x measured speed up on the cityscapes dataset with even better accuracy. So here is the throughput. So here is the latency. These are all measured latency. Not only for ImageNet, but also for super resolution, which is a very critical application in NVIDIA GPUs where we have this DLSS service. So we believe this high resolution prediction is very crucial. Efficient VIT achieved about 6 times speed up, okay, compared with the baseline, including swing IR, restore, etc. And also we enabled the accelerated efficient VIT SAM. Okay, SAM is a very useful application for AR, VR, data annotation, and image editing to collect good data sets. It has a big image encoder, a small prompt encoder, and a lightweight mask decoder. So the original demo has to run this image decoder offline, but we enable this real-time demo locally. So here with the efficient VIT, we just replace this image encoder with the efficient VIT encoder, and the remaining is the same. And we can effectively get 48 times speed up without any degradation of the COCO MAP. Okay, so this is the A100 GPU tensor RTFP16 throughput. This is the x-axis. This is the zero-shot MAP on COCO. This is the y-axis. Here is the original SAM running a single digit images per second, around 10 images per second, maybe. The efficient VIT SAM XL can even get a better accuracy, the better MAP with 16 times faster. Although different methods like efficient SAM, edge SAM, mobile SAM all have accuracy degradation. Efficient VIT SAM has no accuracy degradation, but much higher throughput. And this is fully open sourced on the GitHub. Feel free to try it out. So this is original 11 images per second. This is 182 images per second. You can see the segmentation quality is very well maintained. Feel free to try it at evitsam.hanlab.ai. Here are some more demos, including this very thin ski pole. If you give it a bounding box prompt, it can also segment it very well in blue, despite it's super thin, and also different other cases as well. For segment everything, can get a very detailed segmentation of all the objects in the image. And recently, we also tried efficient VIT for medical images. So this is the ground truth. This is the SAM. This is the efficient VIT SAM on the third row. Not only do we have 700 images per second compared with 11 images, but also the quality is much better than the original SAM, as you can see here, closer to the ground truth. And here is the quantitative measurement of the segmentation dice score. This is ours. And efficient VIT is quite widely used, used by NVIDIA, used by PyTorch team, and also used by AMD, many different projects. And finally, let me talk about controlled image generation. For example, we want to use text prompt to control the diffusion model to make it into a productive tool. So how do we add control? There are several approaches in the past. For example, using here we add the condition by turning into the scale and the bias and control the feature maps by multiply and add. Or we can use the cross attention to add the control. But our approach is to generate new weights to add the control, like the class control, text control, timestamp control. We add a control by a hypernetwork generating the weight to add conditions in the weight space. A simple case, you want to generate a cat versus generate a castle. They might require completely different models. That's one of the hypotheses. But actually we have only one model. Then how do we deal with that? Rather than maintaining one model for each task, and determine which model to use based on the input prompt, like you have a router, like MOE, we just want to have a single model, okay? Because in practice, it's infeasible to maintain a model for each case, but can be viewed as efficient instantiation of this approach, because based on different conditions, you can effectively generate different weights. And here we have a hypernetwork which generates the weight for the diffusion model. Okay, and here we keep the base static, the base weight to be static, and we add a bypass layer to generate those conditional weight. And we only need to generate for a few layers, including the output projection layer and depth-wise conv layer and the patch embedding layer. Okay, making all the weights condition aware is not optimal because it has a lot of parameter overhead, making the training process much more difficult. And here we combine, we compare the baseline UVIT or the DIT before and after using CAN. Actually, we can drastically reduce the FID with the same number of steps. And here we consistently have higher clip score for both UVIT and DIT. And here we combine this marrying this CAN with the efficient VIT and produce this ZAT. Okay, using CAN to add the conditional control and also using the efficient VIT as the backbone. And here we came with this new diffusion model architecture. And as a result, we can reduce the number of max by 52 times, which is actually huge, while decreasing, even improving the FID with an even lower FID compared with the original DIT. And this is rendered with ImageNet 512 by 512 with 52 times less computation cost. And this is text to image generation with 6 times less computational cost. Okay, so that concludes my second part, efficient long context generation and also efficient large resolution generation. Okay, we first introduced streaming LLM for another attention sink phenomenon for long generation and also the long LoRa for efficient fine tuning to increase the context length. We introduced the district fusion, adding a new distributed inference dimension for multi-GPU high resolution image generation. and also efficient VIT and efficient VIT SAM, which is a very fast backbone for vision transformer. And also finally the CAN, efficient technique to add condition to the diffusion models. And finally, we want to highlight this efficient ML.ai course, which I already offered twice. It's going to be offered again this fall. It'll be fully open to the public. Will be live streamed on YouTube, covering the efficient inference technique, efficient training technique, and particularly application-specific optimizations for LLM and diffusion model in particular. Welcome to enroll the course virtually or attending in person if you are local in Boston. All right, thank you. That's all for my presentation. Glad to take questions.
I have a question on large vision models. For deploying large vision models to like the resource constraint environments like embedded systems, devices, what's the reduction in the memory percentage you observe?
I didn't quite get the question.
What's the result? Could you repeat it?
Say it again.
So before deploying the NPM models to the resource constraint environments like embedded systems or HTMLs, what's the reduction in the memory percentage you observe?
Sorry,
What's
I
the
cannot understand
reduction?
Could you just come?
Someone can repeat the question or interpret the question. I just cannot understand the accent. Would you mind rephrasing the question? I cannot hear it very clearly.
So, like before deploying the large vision models to the resource constrained environments like edge devices or like embedded systems, what's the reduction in the memory percent you have observed for the LVM models?
Sorry, I just cannot understand your accent. What is the question exactly?
So before deploying the model, was the reduction in memory consumption that you observed?
Yeah.
So
you want to just type
for
it?
Llama 2 7B require 14 gigabytes.
Mhm.
And after AW quantization, it requires 3.5 gigabytes.
So thank you, and I have one more question. So I guess you will also be quantizing the convolution layers, right? As it is an LVM model. How are you quantizing the convolution layers? Like most of us
No,
know,
we are
like
not quantizing. No, we are not quantizing the convolution layers. As I mentioned, the majority of the computation is in the large language model, not the VIT. So we didn't quantize the VIT, but only quantize the large language model. Since large language model occupies more than 96% of the total latency.
okay. So yeah, mostly smooth quant is for the for the cases where there are more outliers in the activations, right? But in most of the cases, LLMs contain more weight loads rather than the activations. So in those cases, like how are we applying the smooth quant over there?
You
Like
mentioned actually, LLM contains more what?
more weight loads rather than activations. Is it something right? Like LLMs have more weight loads over activations.
Oh, I already presented that. That's the AWQ to quantize the weight to 4-bit
Okay.
and keep the activation to be 16-bit.
Mm-hmm.
And that also requires similar approach using this mathematical equal transformation to scale the important weights. So rather than using FP16, you can scale up the weights if the activation is large. And we find scaling up the weight will effectively protect it from quantization error.
Okay. Yeah, got it. Thank you.
We have one more question.
So, my question is that for AWQ and smooth quant, as you showed that if the activations are very large, we just scale up the weights, but the activations are input dependent, right? So, so the same activation might be low for like same position at that activation might be low for a different input and might be high for one input. So how can we uniformly scale up the weights depending on the activations?
So here, as you can see in the plot here, across different tokens, the fixed amount of the fixed channel exhibits this outlier phenomena. So the very interesting phenomena is that the outlier channel is persistent across different tokens, different inputs.
Okay.
So this is the same channel, like channel 1000, channel 2000, channel 5000, no matter if it is token 100 or it is token 300.
Okay. Okay. Thank you. Thank you for clarifying.
And the only special token is actually the sync, attention sync token, which require special to be specially taken care of. The first token is usually very heavily attended. So in Llama 2, we also observe this, the first token is very crucial.
Thank you, Dr. Han. Since you're talking about this attention thing, my question is about this as well. So it sounds like it's more like a happy coincidence that we haven't considered the in the cases where the token is independent of previous, so some place that we need to detect. Do you think, how do you vision that as a model design? Do you think this is, something that we can take advantage of, or you think is some problem that we need to solve is in these cases?
Yeah, that's a good question. So we tried to, when we are doing training from scratch, we have a learnable sync token and appended to the beginning of each sentence, and we can effectively using that learnable attention sync, just like you provide a dedicated attention sync. Okay, so in that case, we find we don't need 4 attention sync tokens, wasting 4, but still we need 1 token. That has to be sacrificed as attention sync, plus that extra dedicated attention sync token. But that was actually trained on a relatively small model, several hundred million parameter model. Maybe if someone have a larger computational resource, using a dedicated sync token on training it on a larger model might be very interesting. But on a small scale, we did observe the improvement by having a dedicated sync token.
Thank you very much.
Hi, Song. Anish here from Georgia Tech. Thanks for the really great talk. It was like a crash course. Learned a lot. So I have a question on the attention sync as well. So it makes so the reasoning of why this first token is very important was really insightful. I'm wondering if you think there are other tokens which are just similarly important, because there has been recent work, right? Heavy hitters and so on, where they talk about some tokens are really important and you should really cache them. Do you think there are also some like reasons behind them rather than just being important in the current context?
We try to explain this first token because that's the only one where that is globally visible. Like the second one can see the first one, third one can see the first one, the fourth one can see the first one. But we do feel, we do observe several scenarios where heavy hitters fail. For certain tokens, for certain contexts, one token may be a heavy hitter, but to generate another token, it may not be a heavy hitter. So once it's pruned, it can never come back. It doesn't quite work. So I feel this still require, except for the first token, which is for certain to be super important. For all the later tokens, they're not always the heavy hitter in different contexts and different new generated tokens. So I think it's still underexplored.
Gotcha. Thank you.
Thank you. I think that's all the questions we have. Let's thank our speaker.
You.
All right. I think we are getting into our panel session now. Raj, do you want to take over?
Try.
Yeah.
Okay.
Which one?
I think this is called panel. Refresh it.
Hmm.
Google DeepMind, Tatiana from Modeler, Sri from Dmatrix, and Hawkman from UCR. Come over. So the theme for today's panel is we'll take a little bit of detour. We talked about whole day about LLMs. By the way, before we go, I want to introduce myself. I'm Raj from Meta Infra Group. I work in MTIA. So today's panel topic is AGI, artificial general intelligence. And as we know that this is a very speculative at this moment, but we still like to understand what different challenges could be, what are the different paths to it. And we know what the AI state is today. It's not at, in many sense, there are many gaps, but then how do we fill those in? Do we even understand what this actually means? So, so I'll give you a little bit context about how we will conduct this panel, and then the first of all, we want it to be very freewheeling discussion, meaning that this is where people interact, but we'll have two parts. So first part is the structure part, where our committee has decided few questions. Again, panelists are free to kind of paraphrase those questions, change the context, and provide their input. But I'll read out the question. Panelists can pick who is going to answer, and others can talk in support or express their opinion and views. Second half would be where the audience would basically, so we'll set up the base in the first half, and second half, is this working? I can pass this to. So one of you can keep it. So second half would be more where panelists would actually discuss, where people can interact with them and ask questions, either challenge their position or other panelists can also challenge each other. So to begin with, let's ask the very basic question, which maybe when we go to sleep or we are about to go to sleep, we ask what AGI is really. You're working whole day on LLMs and AI, but what's the next step is? Do we even understand? So my question to the panel here is that what really AGI is and how it is fundamentally different from what we have today, which is we think, let's say, trillion parameter model, LLMs, and Gen AI type of workload. And so this is kind of open question, and we like to understand. So anyone wants to take on that?
If it is published actually in the Journal of Physics Research and the fact that it can have conscious behavior in studies, which means when it's used. It's a theoretical, psychophysical, psychophilosophical take on how consciousness, a concept of self-observation, could emerge in AI. And well, let me say that LLMs are not it. So the idea that we propose there, and let me build up a little bit, in terms of what is consciousness. So the first order consciousness is that you have a state of mind. And you know that you have a state of mind. Right? You're aware. The second order consciousness is that you have a state of mind. You have another state of mind that observes that state of mind. Like when you're thinking, that's thinking about truth. That's called second consciousness. There is a social aspect, social, physical, psychological consciousness that has been discussed, and that is like, consciousness emerges in interaction with the environment and with other, conscious entities. There are tests like mirror tests, which they cover, or paint part of the baboons like pigs. And they want to see if that baboon will recognize it. Only, high-level primates can actually make that distinction. It's still debate. So in that paper, we argue that, well, all of these, theories that have been put forth, generally trying to describe what our consciousness is as human beings. They don't necessarily go to a mechanism that can generate consciousness. But when research from CMU and then Joshua Benju is like actively, working. Our theory, which I developed by, in equal contributions with one of my dear friends, Professor Liza Wajji, Kansas State University, said consciousness actually does not emerge in solitude. You cannot just build one model, for instance, and say this is conscious. Consciousness actually emerges in communal interaction and in communal environment. And the way that we propose that we could, and takes a little bit from the evolutionary biology, is that when two agents can create a language through which they can communicate time-varying symbolic state changes within themselves together, then they both become collectively conscious. I'll get a little bit into it, a little bit like, that's formal definition. Not individually, both of them. That's like the minimum requirement. So let's look at a primate who is evolving to become a human, right? We start creating language for ourselves. There are debates whether the words that we choose to describe things are important or not important, but let's assume that it's not important. One of the kinds of the words is a noun, which is a static concept. There is no temporality in it, right? An apple, a tree. There is no temporality. But it's very, 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 very hard to think about words because there is a temporal aspect to it. So that is with respect to external events, when you say something is wrong. Right? Another level is that when you think, I am thinking,
I am liking. I am disliking. That's when I say time-varying symbolic state changes. And the ability to create that language on your own, not copy the language or create a computational memory out of each of the elements, right? To be able to communicate that with the language that you have created with the partner, you become conscious. Why this matters? Because that is a pathway to empathy, which means, well, empathy in a fundamental manner is not a possibility, because none of us actually can experience the world from any other person's perspective. But you can feel it. Let me give you a little bit of an example. When I say I had a delicious food, the word delicious invokes a representation in your mind, not your brain, your mind, which is the higher level of representation. But your experience of delicious is vastly different than my experience of delicious. Probably goes back to your mom's cooking.
So I think that's a pretty solid argument, and I think most of us would agree. Anyone in panel want to add more to it or want to challenge that for just? Sure. Sure.
This is interesting. Then when you think about meta concepts, there are concepts that are physical concepts and they're tangible. There are meta concepts that are not as tangible. I'll start with tensors. Then love, hate, God. You all have a mental representation. But think about what that actually means.
Okay, that's pretty solid argument. So anyone else on the panel? I mean, this is again, you can add your own thoughts to it, what your understanding is, and people will benefit from it. So that's no right or wrong answer. It's the perspective we like to hear. So Amit, you want to take up on?
Before we get to that point about consciousness, if you want to take a step on top of these LLMs and machine learning application, there are still a lot of other features that they lack, regardless of having this kind of notion of consciousness. One obvious kind of a step is planning, memory, and how these machines can do these tasks. As a human, like we have like a sense of planning, and for many tasks that we do, and right now these LLMs cannot do this planning for themselves, and they don't have this sense of memory of kind of leveraging the past experiences. I think if I want to connect to what Ali said about consciousness, I think some of these features might lead to emerging capabilities like consciousness. Or not, I don't know what's happening, but it's still, I think, to get to the consciousness point, we still have a lot of other steps, other obvious steps that we can take to maybe reach a semi-human level of intelligence.
Okay. So anyone else? Again, this is a very basic question, so we like to hear everyone's perspective.
Then, what it means to be AGI is very different. If you add, emotional intelligence along with cognitive intelligence, it's a ballgame. So even with cognition, if you think it's human and you want to be better than a human, you want to be in a state where A human, they're learning in their environment. I think somebody mentioned it as well, right? There's an environment where you're continuously learning, and it is not like you're once and done. And then you are allowed to forget things. So it's okay to have catastrophe forgetting, and it's okay to relearn something. So these are all things that we are kind of uncovering in elements and discovering what they can do. So it's more like scratching the surface versus saying, we want to get to a state where they can be better. And to me, it's API is a proxy for what that is, getting these models to be better and get closer to what humans look like.
Okay, Hakun, you want to share your thoughts? Yeah.
I think, yeah, my name is Hakun Khan, assistant professor at UCI. And I think a lot of very advanced topics are being discussed, and I really agree with what discussed so far. And yeah, I have been thinking about the definition of AGI as well. And I actually have a basic question. So how should we define AGI? So where is the human in the definition? So do we need to define it from the human's perspective? Then what would be the way to define it? So it gets back to the traditional Turing test. So the traditional test try to distinguish if the given program is a human or the AI program, but that involves the human in the loop in the definition. So my question should we consider the human in the definition of how we define AGI or not? Then if so, then how should we formulate it? So in addition to what I've discussed upon, so I wanted to add this question for further discussion.
Okay, Tatiana, your thought?
I'll skip this.
I will come back to the second question. So I'll pick up from what Sri said. I think defining it in such a way so that we can tackle and build systems around it, which can actually mimic some of these capabilities, is very important. So the second question is that looking at the need of what to build this conscious machine or agents, the kind of, let's say, if we define them in compute, memory, and other kind of requirement, what sort of do you think the system and solutions we have to conceive to actually get to that level? Are we 10x away? Are we 100x? Are we 1,000 or don't even know? So in talking in terms of systems and solutions, which may mimic some of these capabilities, what's your thought on that? I know Professor Hadi, he takes great pride in thinking through NPU, right? NPU was the term he coined, he claims, at the very beginning. So I like to hear what kind of NPU would you build which can exhibit some of the AGI related capabilities.
Yeah. But disagree on the definition I propose one, you might have something else. That's one thing. The other part of it is that, well, what is the end goal when that before even we get into design stuff, right? So I would assume that when we were building tools, we want superhuman performance. We don't want human performance because human performance is here. You already have it. And depending on socioeconomical situation, it's cheaper or more expensive. Right? So we want to get a superhuman part. Second stage of it, if we just take that utilitarian aspect, is that we have to first realize whether or not LLMs are in the right paradigm. So that when I'm building my system, I'm actually working towards that. It seems like there was a little bit of a general notion that yes, there is, but there are some things that we can patch. I encourage everybody to go and look at Thomas Kuhn's book on scientific evolution and how paradigm shift happens in science, but in a breakthrough. This was a breakthrough actually. We are in a new paradigm. Does that mean that we are actually going to get there? That's a big question. Whether or not we're getting to superhuman performance. I'll give you one example. ChatGPT or any of these large models, they're very myopic learning instructors. That's why we don't feel that connected to them. They do very good things for you, but you don't connect. Third part of it is that, well, let's say we even conquer this and we find what is the ramification of that for me as a human being and for the machine itself. Can you delete an AGI? So that consider getting something. Why carbon waste? Intelligence has higher level, order over silicon. And the fourth point, I'm going to come back to empathy. Because if you build machines that do not have empathy, then we're moving to towards psychopathic machines. That's different extra, definition. I do firmly believe that LLMs are not it. Right? They are a step forward. They're not, that step that we. And to answer your question, come back, backtrack. I would actually think the problem is building the next thing. The problem is actually re-architecting our cloud infrastructure such that we can build an amalgamation of classical, symbolic, and deterministic language with a collection of expert elements for them to deliver end-to-end applications that we are good at.
So let's suppose, let me pose the question there and to others also. Let's say we need 1,000 x better memory bandwidth or performance. How do we actually get to that? What kind of solutions can we think of, even 100 to 1,000 x range in terms of power efficiency, in terms of bandwidth? Many of the LLMs are already getting into there. So if LLM are not the way to actually evolve this further, which I doubt, I mean, it's still early. So any thoughts on that aspect, building the cloud infrastructure for? It's off.
So much in the future, but looking at practically going to the title of this workshop, energy costs are not sustainable to train and run models at the scale which is required to get a GI. And so we need to learn how to do things more efficient. And efficiency comes from innovation. And we have a lot of people working on accelerators for AI for a long time, but let's look around. How many LLMs are running accelerators? And the answer is very few, right? Especially if it's not a big company like Google, which has its own proprietary hardware. So the problem here is that we can build hardware. We can program hardware. We cannot program new hardware with the efficiency we can program CPUs and GPUs, which have been around for decades. And we can build new architecture, new model architectures, but it takes so much effort to make them run efficiently. And so I think the problem that we need to solve is to improve efficiency of the whole field, so that people who design accelerators, build accelerators, and deploy accelerators on the same scale that we write software.
Okay, anyone else wants to add to? So a little bit on that. I mean, the current hardware software co-design we see today and the kind of system we build today, if let's say as you kind of get a sense what AGI would be, how disruptive it would be to actually to tackle the need for the AGI type of workload, if that magically appears, let's say in 3 to 5 years, like a ChatGPT as a moment, we don't know if it can happen for that or no. Some model researcher might find something interesting, but in that sense, do you think it would be too disruptive, or otherwise it can be rather? So the thought process is, would it be evolutionary, which means what we have today and it will evolve from here, hardware, software, both, or would it be revolutionary where, this is kind of hit the roadblock, and you have to really think through if you have to tackle this problem in the right manner? So the question really is evolutionary versus revolutionary. What's your thought for AGI as in solutions and systems?
It's like any other discipline that you have the evolution of science. We are a scientific, endeavor, right? So a paradigm shift happens. A breakthrough happens, a paradigm shift happens, that has happened, but it doesn't resolve all the problems that you have, right? You start patching, like you told me, you start patching. And then you get to a point that is not answering my questions or doesn't model the world the way that I want it. And that's where you really expect that, another paradigm shift happens. I think, like, coming back a little bit to reality, I think the problem is not just the hardware. It's actually the entire system organization. Our system researchers, our counterparts in the system research community, they have done a magnificent job of abstracting the cloud as a function of it. That's called serverless. That's pretty amazing, right? So you imagine the whole apparatus that runs the cloud, and you submit a function, you get the result, you submit the next function, and it happens, and everything is just being done. But that cloud infrastructure has taken a very evolutionary path forward. That's one. So one of the things that you mentioned is very important, is that how do we actually take our innovations in the hardware domain and go back in integrate. So there is a possibility because, well, they are changing the system software behind certain abstraction. We don't know what's going on. I mean, as a pedestrian programmer, yeah? Why not change the entire infrastructure? So I think there is a revolution needs to happen in our cloud infrastructure in such a way that we increase the efficiency, as you said, across the board. Right? And that's been going on. Like we have this aggregation now that's happening. We're embedding computing in every aspect of it. But there is an impediment. It's a very important impediment. And that's the economics of scale. Let's say I'll talk like after this panel, I'll talk about some of my work that I've done, like designing, anybody is taking it. The reason being is that the hardware design cycle is extremely long. And even after you design it, back-end engineering to get a chip working, that's the nightmare. Right? Dartmouth had a bunch of programs on automating. So, this whole machine learning for CADs and things like that came out of that to reduce the cost and the time of actually getting to a chip. That's one aspect. But the other part of it is actually, again, I'm going to come back to it, is that how do you embed that within the system, both in terms of infrastructure and the software stack that exposes the entire data structure two ways as a unified Kubernetes cluster or a function. Right? And I think that part of it, you mentioned something, which is like, let's say we get 1,000x improvement in the bandwidth. Well, one thing that we have to realize, well, there are certain physical limitations. We as computer scientists, we used to be gods in terms of our computing. We simulate everything and we can change the parameter, everything just changes it. Reality doesn't work. There are certain constants. But what really matters, I think, is that now the definition of the compute node has been abolished. You have CPU as the central processing unit. You have this, you have network, you have DRAM. Everybody has a very specific task. Now you're talking about near memory, near storage, in-network computation, right? So while we're talking about it, what is that computational core that we can contribute in any of these components, not necessarily relying on a single one. That's a neural network. And I'm going to do a plug, cross-domain multitasking. Because end-to-end applications are not neural networks. It's actually a composition of different, domains together. And even if we take a practical, utilitarian, evolutionary approach towards getting that system payoff, we need to really move on from this myopic focus on neural network and see how we can solve this, both in terms of defining an acceleration pool that is economically viable to fabricate and integrate them while considering data, motion as a problem.
Okay, so let's go around and ask one basic question, which is now sort of getting to more reality. Let's say cloud infra is going to be the current cloud infra. If you have, what kind of major bottleneck do you see and what can be sort of solved? So let's say one major, which to improve really 10x 100 performance. Because if that is the evolutionary path we are going to take for a while, I'm not saying forever, but what do you think in current cloud big companies, what they build is the major issue is? Because it's still not meeting the demand. As the models are increasing, you are throwing more and more GPUs. They are consuming more power and energy. So how can we redesign, or any thoughts on that? So to everyone, actually.
Maybe I can add some 2 cents on that. So I think everyone knows that currently the ML workloads such as LLMs are heavily memory bound, and we need to utilize multiple GPUs for running a single inference for large models. So my thought is, yes, the memory side needs a lot of innovations, and actually many things are already happening. So as I mentioned, so there's in-storage processing and near memory processing. So and also there are some innovative chips such as the chip from Grok, so which dramatically changes the computation and the memory balance within a large chip and try to address the memory bottleneck. So I think such an innovation is a kind of positive direction the community is going. But basically, I wanted to highlight the memory is the main challenge for the latest workload related to LLM.
Okay, so I think others, if they want to add.
I think I want to answer the evolution versus evolution part first. I think if you look at like how we as a human reach to the level of AGI that we think about it, I think we had a kind of evolutionary path, right? So we had this long years of self-improvement and self-assessment and improving and improving.
But let me interject. Sure. You don't want to go that path when you're building for ML and AI these days, right? You don't want it to be another 100,000 year and then find out something. How do we?
So I want to kind of answer that question. I want to get it. But on the other hand, when we want to kind of reach the technological advances, we cannot only rely on this evolutionary path. But as you said, it's a very long process, right? So that's why I think it's not going to be a one solution. It's not going to be only an evolutionary path. Of course, we need some disruption. Both, I think it's not only a actual system. I think it's not a very proper question to only think about the system aspect of it. We need neuroscience advances. We need cognitive science advances. We need robotic advances. And then maybe collectively we can reach the point that we can call something AGI. So to answer that question is that we need an evolutionary kind of aspect of it, and all of us more or less working in that direction. And in this path, of course, we need some revolutionary aspects. Like a very, very obvious example is transformer paper, right? When I joined Google, actually the team was working on the transformer paper. And there is a rumor like that I heard is that actually no one was helping them in the sense that they were working on this path for like more than a year, and they were optimizing their code, and no one actually believed that such a thing could be such disruptive and such transformative. And a paper came out, and a couple of years after, you can see that everyone's talking about LLM and how we can optimize it, how we can scale it, how we can make it system for it. So we need to go through the path of evolutionary. And I think in this path, of course, disruptive in terms of technology, in terms of how we think about different scenarios emerges, and we hopefully can reach to the definitely to the AGI that we expected.
Okay, so if anyone, okay, so now we are very much into the unstructured part of it. What we would like to do is let audience to ask questions either to panelists or what they said, either to challenge their opinion or ask something new. So this is more freewheeling now. I'll take the back seat. Or other panelists can ask each other as well. Okay.
What we can learn from this transition. So if that's tomorrow, that's none of the next generation of model, how we can handle those new innovations from algorithm from, the support of that, what can we do from that system of technology?
I think the big question here is, are LLMs sufficient to take us to where we want to go? Or are we going to get new models, and are we over specializing all of the infrastructure today for LLMs? A lot, like the whole software stack was built initially to surfacing like convolutional neural networks, and then we've had to go back and rethink all the assumptions which have been made at the system levels, like no state shapes are not static. But I think that path, as usual, is going to be evolutionary. We are going to continue building what we are building, then something new will emerge, and then it will grow, and then one day OpenAI or somebody else. Or that's what I'm saying. Somebody will find the use case which makes the rest of the humankind realize what's up.
So top of that, OpenAI is asking for $5 to $7 trillion to build the chip. Any guesses on what kind of chip would they be thinking about, or any wild ideas?
Are we going on other things that are out there? And challenge the assumptions in the software stack and the modern architecture, transform on because so what would have happened if we went for another architecture? Would we have, is it all serendipity because of that? I would challenge that we need to be more like this allows us to do something out of the box by breaking assumptions and challenging those assumptions.
I'll add one thing. I have to correct one thing. Language is not developed evolutionary. Actually, if we look at the timeline that language has appeared, it's too short for the evolution to actually begin. So there is a lot of data. But I would say that the lesson to be learned, don't over-invest in a product. If the researchers who actually came up with the transport model, we're just trying to somehow fix this convolution to natural language processing, which never have happened. So right now, we just like everybody, I'm going to publish papers, don't go to the game, right? It's just don't better than give room for thinking what a new paradigm. Yes, we will do evolutionary research. We're going to go after the evolutionary thing. There's nothing wrong with that. But if you don't take the mindset that this is not right, I want something completely new, nothing will happen. That's how I said, everybody in this community, look at the number of things that have been published on conclusion knowledge. Way by yourself. Should we continue doing that and check what is going to happen next? I don't think that's the right.
So on that side, let's say, when do we know that certain field is somewhat saturating? For transformer case, I think CNN started plateauing their top one error, and I think transformer with the VIT and other, they had better, even LSTM for RNN, right? So I think that moment was clear that this is saturating, we need something different. How do we know LLM is saturating, or when? What are the indications?
Why to wait until it's saturated? Right? It is going to saturate.
Okay, so
That's the definitive answer, and that's the, like, generally, that's the positive side. You're all waiting to come up with a breakthrough, which means that this paradigm is partially true. Let's just put it aside. We have a new paradigm. That's how we cure cancer, hopefully, in the future, right? We know it's gonna happen. Why do we have to overinvest on it? There is profit to make. And that's gonna drive the economy, of moving forward to this evolutionary pattern, like the evolving, that's bad. But as researchers, I see a lot of young people, right? Why do we have to wait up? We know it's gonna happen. Why don't you come up?
Okay, yeah.
Yeah, I have two questions. One was about, like, some of you mentioned that there is a problem where, like, you can develop software quickly, but because there is, like, developing the hardware is much more harder, not just because of the, I guess, process node and all the manufacturing limitations, but also because of the adaptations. Like, it's not that easy to program a new hardware. There are a whole bunch of pipelines that need to be built. So what are, like, I would like to just, like, share your thoughts on how do we go about sort of that? And I also pose a second question, like, separate question is, there has been this talk about, like, industry basically driving out academia out of these kinds of research by just sheer economic forces, where you actually get most of the academia cannot have, like, cannot easily get access to, and I think you mentioned that in the talks, do not get access to much of the complete resources that actually can get. And I guess another question on that, I'd like to discuss, like, hear your thoughts on how do you counter that.
Yeah, maybe I can answer to the second question because I was once in the industry and moved to academia. So I understand the research going on in the industry and academia. So yes, industry has a lot of resources, but that doesn't mean that we can do anything we want in the industry. So there are many contexts depending on your org and your team. So, and there will be some business goals. So there are many factors other than just research ideas. So your direction you could explore may be constrained by some other factors than just technical factors. So that's one thing. And in industry, yes, but in totals, they have a lot of resources, but that doesn't necessarily mean that you particularly you will get the sufficient resources. So you still need to justify your research and request the resources for your research. So I think that process is pretty much similar as what's going on in academia side. So in academia, we write grant proposals and request for resources for particular ideas. So I see a lot of similarities from there. And also, it doesn't necessarily mean that academia cannot do large-scale research. So we can always collaborate with industry partners. And as far as in my experience, so many industry researchers are very open to academic collaborations, and and they also often have some research programs. They take the proposals from the academia and open up their resources. So I can think of several examples, such as Google also provides quick view for the research project, and AMD also have offering the computing infrastructure for research proposals. So in short, in short, the industry doesn't necessarily have the full capability for driving all the large scale the research. Academia also can do it, and also industry can also have some constraints. So I wanted to highlight those differences and similarities.
I'll take the first question. I actually have been working for around 10 years. I'm automatically generating accidents. Run through many generations of them. And through which it's not that we generate one single accident. We actually can generate, shrink, make it bigger, make it smaller, depending on your use cases. They actually have a tutorial tomorrow. On Genesis, which is for generating systems and architecture for acceleration. And this is probably the third, fourth generation. That's one way, and there has been some research. I think I started at the Tabla, which was the distinguished organizations. So I have heavily invested, and it's been we raised like more than $10 million, like to support that. And now it's completely open source available. That's the second. Software moves fast because there's a humongous open source thing that happens in video. And we as researchers, we need to contribute. We're actually, not only we build the hardware, we actually build the compiler for it. We're actually updating our language and the compiler, and we're taking Glasshouse design efforts right now. Every week we have discussion, it's posted online immediately. We can see how we are evolving on compiler and hardware generation. And the hardware generation, I'm very proud to say that we can do end-to-end neural network execution, especially to make it. We have a paper that's Jewish present Tuesday, and I'll talk about it during my talk. It shows how you actually do end-to-end neural acceleration beyond the principle. And that's also parameterized streamable expandable. And we can target applications like I have an NIH problem on training platforms, full kernel power, to high-end storage serverless computing with the same platform. We generate the hardware dramatically. There is a backend issue, but the CAT community is actually working on it. Startups on it. There have been development programs on, that, which is another issue. I'll give you this example of Verilog and the multi-target, compiler that actually compiles code to variety of the configurations that it can do. Like, Genesis platform. I want to plug it, but you just make me.
So on that front, Amir presented his talk, and he also talked about using ML to build hardware. I mean, one thing is with the less even simulations, which mimic your hardware, is this taboo where you're more willing to contribute to open source software than actually hardware. Now, within a company, you can build one kind accelerator, and let's say TPU Google builds, but Microsoft builds something else, and so on. How do you actually encourage people to be, because you need a lot of data to train. If this model is, I was about to ask how many simulations did you train? You said 40 million, but I don't know if that is enough to actually get you. Many of these are trained on billions of, let's say, inputs. So how do we actually speed up that? Let's say we do want to build a really good LLMs to actually spit out a better hardware. Do you see a way to either expand within a company? It may not be, it has to be multi. Then what kind of things can we think about to actually ease this? Because as of today, if you go and ask for anyone simulations, they will never share it. Google itself will not share it, right? So what's your thought on that?
I think data, of course, is a very important part of the training process or learning process. I think there are actually the community, especially the hardware community. I think Google has started something in Ansel of the we are trying to it was open source project, but it was part of Google's concept. We are trying to, of course, Google is not going to share their proprietary data, TPU, whatever we're doing. But what's going to happen, we can support and promote the open source community, building some small module. We don't need to establish something that's as complex as TPU or GPU or something like that. We can establish some small module that the community can build and share the data with everyone.
So on that front, let me, I think NVIDIA did very early what called NVDLA, but that was very small project, as in that is like a drop in a bucket. If we do have to scale it to the accelerator, what we build today, even academia or industry, what's the right path? So
it's very complex.
I'll carry on your thought if I'm sorry I interjected.
No, I think like NVIDIA, that was I wouldn't say it's a small project. I think actually it was very complicated, and it was had a lot of, it had the compiler support and software stack support for it, right? It's, of course, it's not the end goal, but it's one step forward of how we can collect data. And I think actually I applaud NVIDIA that they released such a thing. Of course, it's not their end design, but it's something for the community to build upon.
Right.
Yeah.
We can take up more questions. Yeah. We still have 5 minutes. So
this that goes back to questioning the prices. some of the features that you guys mentioned on what could become AGI, like we've seen glimpses of that already. For example, we've seen planning and auto DBD, and DBD5 is most likely rumored to be an agentic workflow. And we've seen like 3 days ago, ChatGPT actually memory across many channels, they have stored things. So given that we are not able to agree upon one definition of what AGI is, we're likely going to end up in a place where one group claims that this is AGI and the rest of us, or rest of the groups going to say this is not AGI. So given that's where we're going, should we even spend time in defining this arbitrary boundary of what AGI is? Is that going to change anything? Because Llama 4 is going to come out, GPT-5 is going to come out, Gemini 2.3 is going to come out. So what is defining this boundary even actually?
I mean, there are good things while there are bad things while. Defining something gives you an explanation. Like actually, the definition of artificial intelligence, comes from Shannon. There was a document in, MIT, and that's like during that document they came up with the definition of artificial general artificial intelligence. It gives you an aspiration of to words. That's one way of it. The other part is that I guess I agree with you in the sense that, well, why do I have to know what I'm working? I just know I want to improve things, like, get things better, like, make it happen. And that resonates with me in the sense that, diversity of opinions and views is actually very constructive. Like, let's say Facebook just went through this whole open source business, and like, OpenAI is dropping model. So they have each their own utility. Why do I have to pick this one or the other? You see what I'm saying? And maybe the conceptual element. I like to think about things in a Hopkian perspective. That it's good to have one extreme and another extreme that don't fight distributed.
I think so. But AGI technology is not like other technologies that I think anyone can come up with their own definition. I think, for example, like we can easily define what is RTL, what is compiler, what is architecture. I think for AGI, it's actually can have a very societal danger if a company can kind of define, oh, I reached AGI. It can have a lot of economical kind of impacts. I think, especially for AGI, we need a much higher level of definition from policymaker. And companies, to some extent, Google actually recently published something about AGI, level of AGI. And I know that it's public that the companies are working together with the government to define some sort of AGI. Because that could be very dangerous. Let's say, I'm not going to call my company, but if company X and comes and hey, I have AGI, it can have a huge economical impact. I agree that for innovation, a solid definition could be limited. But at the same time, you need to define some metrics and some definition for, hey, I reached the AGI now. This is the metric, this is the definition.
So the policymaker, you said, I think the policymaker have a hard time getting the regulations right. This is too big a task. Like as in tech, this is a mostly tech thing, right? Which is to what AGI is definitions and creating a consortium, let's say a platform. So that has to happen with industry and academia collaboration, I think. That's my view. But others can say, how do we even define it, right? I mean, what would be the right forum to define it? Who should be the stakeholders? As you said, one is not good enough. They might make it for their own benefits. So how that definition should come about? What's your thought, Tatiana?
Have such profound effect on the society that we want to be able to measure how close we are to that, because we need to prepare us. And to measure, we need exponential growth. With everybody working in the industry, I don't really work in the area of defining AGI or defining the J property. So my opinion is layperson here. But I think we just need to have the set of tests. It's very simple. And incidentally, if you create those tests, then people will immediately come up with models which can perform those exact tasks much faster.
A similar thought on that is, like, for example, people were doing these benchmarking on CPU, GPU, but for ML, there was not. ML Perf came along, ML Commons came along. I think that kind of forum is needed, but who do we start? I mean, we are thinking next edition of this workshop, we'll just get the proposal from people, what the AGI should be even as a definition. That could be a track. Some thoughts on that, we would be happy to hear. So one last question before we break for 10-15 minutes. Okay, quickly. This is getting, okay, both of you can ask quickly and they can answer.
Or the simple problem counts the number of words after this word. They're simply not able to count the number of words in them. So what do you think we need on top of these algorithms? Like, you know, multiple agents, mixture of experts, or better training data? I don't know. How do you imagine reaching the AGI? Is it like simply just LLMs or what? Thanks.
I don't think there is the answer. Okay, your question.
I keep saying that I put forth a definition after, which is creating language. No, those are not. You can make them editing, right? I mean, I have to encourage you to think a little bit outside of the LLM. Because you're just trying to take together and somehow make it, you know, an AGI. Saying that's not an agent. You actually need to build agents, then that definition is clear, right? That they have to create this language that they can communicate what is changing inside them. Then you have actually a type product in. And that's where you should get to AGI. And I can show that it's, you know, biological evolutionary path towards it in human. So that's my proposition. And stop just forcing element by adding like adding memory. It's just like, you know, keep track of what happened in the past. It's a Markov chain we're adding to it. Not that, you know, that's not like, you know, humongous shift that is happening with that algorithm, you know, doing. I mean, that's where, you know, what I'm trying to argue. And I put a definition, and it's very hard to achieve. Right, when the paper actually came out, that these signs of AGI, my, you know, pattern interpreted and showed that based on the definition, that's not it. Does that make sense?
Okay, Satyam, last question to wrap up. Okay.
When GPT-4 came out and the safety report was made public, there was a test that said the model hired a human to perform a test, perform a task, and actually lied to make the human do it. And now this evening we have a talk about teaching what skills to guide models. Should we be worried?
I mean, the models didn't know it is lying. That's the problem. That's the difference between that's what agents, right? You decide intentionally that you're lying. It's just the byproduct of the training data that in the mathematical propagation, there is a sentence generated which is false, like hallucination. And that led to somebody doing something. And then you can twist this that the model lied. The definition of lying is that you made an intent, you planned, and you went and provided falsehood for somebody to go and accomplish something. That hasn't happened. So I disagree with the fact that the model has lied. So, and in that sense, well, there's many things to be worried for. Think about like, you know, the next generation of kids that they have to be shown with this, you know, this behemoth that they have to compete, even for coding.
Okay, so with that, we'll wrap. I'm happy that we have more questions than answers. That was the intent. Hopefully, you'll think more about it. We have a mixer with the EMC group members or anyone wants to attend in the evening. So they will announce it. And we'll have 10-minute break. But do you want to announce now? And then we'll come back again. So here the announcement, and then we can take off.
back at 4:15.
Okay.
Our next speaker is Hadi. Professor Hadi Ismailzadeh is a professor in computer science and engineering at UCSD. He obtained his PhD in computer science and engineering from the University of Washington in 2013. His research has been recognized by his retrospective, highlighting the core of his papers, significance over the past 25 years of his stuff from 96 to 2020. His work is also been recognized by core communications of the recent research highlights, who are equally macro topics, nomination for communications of the recent research highlights, and honorable mention in macro topics, and a distinguished paper award in 1960. These work on Silicon has also been provided in the governments.
All right. I am embarrassed now. So thank you for having me today. I'm going to talk about a little bit. I think it's a little bit like awakening talk, because for many years the community has focused on general matrix multiplication operations, and if you look at the the number of papers that have been published on optimizing these kind of operations, it's kind of insane. And well, there is a reason for it. And I don't want to pick on a specific thing. I actually will, if I move forward. Okay, I have to make sure that I'm actually, okay, so you're doing it. Is this, which one, is this the Zoom or Microsoft thing? Microsoft Teams? Let me see, I think, okay. All right. So I'm not, necessarily picking on anybody. I have, I'm guilty as charged, right? One of those is not to be, retrospectives is actually a diffusion work that we did back in 2018. And the idea is that, one of my students was actually interning in ARM, and he wanted to somehow cram these large models, convolutional large models, into very low power devices, but without compromising the accuracy. And then what we argued in the paper is that actually more than 99% of the operations are actually multiply and add. At the same time, there was research happening in the machine learning community that was showing that if you heterogeneously quantize neural networks, you can actually achieve the same accuracy of as you were, achieving with the, full precision neural networks. And this was deep quantization. So one argument was we're making too much, all of the operations are kind of, multiply and add. And the other one was that, well, we have, variety of precision, in neural networks. For instance, this was from one of the papers that was published. If you keep the first and the last layers 8 bits, and you can quantize the middle layers to 1 bit, and that's an asymmetric deep quantization. Let it, you can do 2 bit by 2 bit, and you're going to get the same, accuracy. You're not compromising on the, accuracy, because if you actually compromise on the accuracy, you're going years back in research. This is back in 2015. So you have two options. You either build a fixed precision architecture, which adheres to the lowest accuracy, like at the time, binary neural network and architecture for binary neural network was a humongous hit, and everybody was working on it. Or you have to take the upper bound on the, the precision, which you're leaving a lot of efficiency on the floor. So what we did is actually we took a different approach. We actually designed a unit, which is a multiplier. We call it a fusion unit, which is a collection of smaller elements, which we call them bit bricks. These bit bricks are 2 bit by 2 bit multipliers. And then if your layer or a block or a tile can tolerate 1 bit or 2 bit operation, this physical architecture virtually at runtime with very low overhead will be composed to 16 multiplied to P operations, and then you get 16x bits level parallels. And this is different. I was very much inspired by the work that was done in University of Toronto by Andreas Moshovas group, but they were doing bit serial, we're doing bit parallel. We're actually, we're harvesting it. Same structure, physical, with low overhead. Well, if you want 2-bit by 8-bit, will compose to 4, very low. And if you want 8-bit or higher, you just compose this together. The bit breaks, very simple, 2-bit by 2-bit. Why we're doing 2-bit, 2-bit? It's just a trade-off analysis. That was the sweet spot. And the reason that we can actually do this is that because multiplication is actually a recursive operation. If you actually sit down and write multiplication, which given the ChatGPT, nobody's going to do it. So, right, you're actually performing for a 4-bit by 4-bit, or even like 4-digit by 4-digit. You're doing 2-digit or 1-digit by 1-digit multiplication, or 2-digit by 2-digit multiplication. So you can actually design a completely, combinational logic that you can drop in instead of a multiplier. And now what you can do is that you can optimize your GM operations at the finest granularity possible, which is the bit level. Do we have more granularity than that? I'll talk about that. Well, that's not the only part of the story. Well, somebody needs to supply the data. Physically, we have our buffers are just producing 32-bit values. But at the software level, you can actually interpret that as 2 16-bit values, or I don't know, I can't do math. So 8 4-bit, right? Value. So with the combination of two, you would actually get what happened is that when we compare our design, I'm not trying to, put NVIDIA down, like they build a chip, we're just doing modeling here, right? So we can actually achieve almost the performance of Titan XP in 8, and that was the high-end GPU back then, right? Within milliwatts. This is not magic. I'm always skeptical of like large improvements. It's because we're actually doing optimization at the bit level, both in terms of memory and in terms of the operations. The question is, can you push it a little bit? Actually, Surush is sitting over there. We did a mixed signal design. The idea was that can we go lower than 1 bit, right? That's when you enter the analog. And then when you actually enter the analog domain, there are issues that you're dealing with. One is that you need to encode more values in the limited range of current or voltage. I'll talk about something else as well. You have susceptibility in noise. Noise happens, you just values are latched off. And one of the biggest problems is analog to digital conversion. That's the humongous overhead that you're doing. As soon as you cross the boundaries, especially from analog to digital, you're paying a humongous thing. For each of these challenges, we actually provided some solution. We use another property of the mathematical properties of vector to vector multiplication to devise low bit width primitives that you can actually implement in the analog domain. Then we use like modeling for noise during the during the training. This is, I would say, a little bit of a hopeful visual kind of assumption that any machine learning person is going to retrain their model because your hardware is more efficient. Like I would take that with a grain of salt. And then for analog to digital conversion, we actually utilize switch cap instead of the current modeling. And also I think we built the very first wide bit vector analog unit for computation. And I don't want to spend a lot of time because my talk's title, I haven't forgotten, is neural networks are not made to small. Right? But I showed you how you can take an individual multiplication and decompose it. If you actually take a vector-to-vector multiplication, you can rearrange the bits of each of these elements such that you perform low bits operation in the same position without the need to shift it. And then, after you've done these wide low bits operations, then you can do a collective shift, put it together, and you get the results. What that means is that I can actually build analog units that are performing individual very low bit operations and then putting them together in analog domain, then you're doing A to D conversion. So you're dealing with the noise that, the value encoding problem, because you're not actually encoding large values in the analog domain. And we're using switch capacitor for doing that. That means that we're actually delaying the, first, I'm amortizing the cost of analog to digital conversion. Second, I'm delaying the analog to digital conversion. And if you look at the, the structure that we have here, parts of it is actually doing the, instead of modeling the, the behavior of the weights and the inputs in the resistors, you're actually modeling it in the charges that you keep in your capacitors. That's called switch cap, right? And if I want to walk a little bit into it, like just look at this two. It's a little bit faint. I apologize for that. So if you look at this unit, right, this is X1, this is X0. So you have two capacitors, two CX in the top. You have CX here, which means that if X0 and X1 are 1, 1, you're going to get 3C, right? If it's 1, 0, you're going to get 2C. Very simple. And that's coming from that harvesting that mathematical property to perform this low bit fit. And then after encoded the values and the charges that perform, you actually perform a charge changing. And the details on the paper, I don't want to get too much into this part of the talk, that the result of the sharing, the amount of the charge that you collect and the capacitors is actually the result of multiplying W to X. And then in the next phase, what you can do is that you can actually, you have multiple of these units. That's the vector unit that you're doing, low bit width interleaved, vector unit, and you can collect it to accumulator capacitor. And by doing that, you're just actually performing large number of multiplications in the analog domain. You're delaying because you're doing accumulation in the capacitor. And what can you do is that you're paying less overhead in terms of the A to D conversion. And you've dealt with the, value encoding problem because you're doing very low bit operation. So if you actually look at the result, you're getting to 2.1 speed up in digital. If you actually do the bit vector composability, right, you can actually do the bit vector composability in digital. You don't have to do it in analog. And you're getting 4.1 speed up in analog domain. If you go to and if you want to do with high bandwidth memory, then you get a little bit more. My argument here is that actually these results do not necessarily justify switching from digital to analog. The benefit is not that big, right? We published the paper, but that's my results. So, and this was the theme of the research that was happening at the time. The reason being is that the presumption was that most of the operations that are happening in the neural networks are actually matrix multiplications, right? So Surush, sitting back, is the former, student of mine, and he's going Apple now, and he's going to present the tandem process. He has graciously agreed for me to do a rehearsal for him by presenting his slides today, in your workshop, which now let's see if that solves all of our problems, or what we can do, what we need to do to actually deal with the neural models that are emerging. Is this assumption that we made and we went and optimized the matrix operations engine to death still holds, right? Actually, if you take a historical perspective on on neural networks back in 2014, even 2016, you see very limited non-gem operation. But as we progress in time, the number of and the diversity of non-gem operations increases significantly. That's not just one part. It's actually they are being interwoven in very complex structures within the between the matrix operation. So if you have an ideal case a matrix engine that is taking 0 nanosecond to do your matrix multiplication. But you have another unit, which is going to take its object or it's not going to model like this. You're actually killing your performance. And our argument is that, well, the research that pays attention to these non-gem operations actually long overdue. Kind of, if we wanted to, go back to the panel discussion, like, don't latch on to something because people are doing it. Let's look a little bit. And the reason that we actually come across this problem is that we actually took the time and the effort to build this. This is part of the Genesis project that we did as part of our, DARPA RTML project, and we have an NIH project as well. To build this, and this is the design that we're proposing here, is something that can shrink and expand and, can be generated automatically, completely. So, as I said, the first characteristic that we're looking at, right, we're seeing growth in diversity. You have element-wise activation-wise, function. You have element-wise mathematical operations that are not matrix operation. You have to do data layout transformation. You have to do type, conversion. You have to do reduction operations in, emerging neural network. And all of this cannot be mapped to a matrix engine. And when I say a matrix, I'm very opinionated about this. I really believe in systolic arrays when it comes to, like, matrix. They're very efficient. It's very hard to beat them, right? And now, look at the progression, in terms of the time. It's the cumulative counting of the number of operations from VGG16, which is like a classical neural network that we started with, right, to GPT-2. The number of the, these operations are increasing significantly. Again, examples, right? Let's look at ResNet 50. This is the, the blues are, the blue is not the ocean. It is an non-gem operation. Then you have MobileNet, you have BERT. The blue is increasing and the blue is becoming, it's structuring much more, interwoven with the rest of the architecture. One of the, characteristics of this, if you actually do a roofline modeling here, which Surush has done, is that you see that these operations are actually more memory bound than compute bound, which is kind of a little bit different than gem operations, especially if you consider timing and reuse. That's when you make gem, like, compute bound. So now we actually have a missing component in our NPs, right? There are two solutions. Right, you either use a general purpose vector processor to perform kind of these operations for you, right? Which, because it's general purpose, you will always have the greater performance. Or you can use the classical way of scripting them, which is that we're going to have specific custom units for each of these operations. Well, when you were just doing sigmoid, that was possible. But now that you're doing these all diverse operations, that's not what you can do, because this is going to lead to either your hardware is obsolete in terms of the models, or you have to go somewhere and do these operations, come back, continue what you were doing. What we did, and this is actually one of my, when I do a little bit of a classical computer architecture work, which was we were sometime in the golden age, age, we had an ISA. We were doing a lot of, innovations under it without touching the software. That's pretty amazing if you think about it right now. Like, we got a chance to actually design and specialize the ISA for non-gem operations. To kind of explain why we did what we did, let's look at this code excerpt that is showing a vector add in a general purpose. So this is taken from RISC-V manual. We're not going against RISC-V necessarily, but that's a good example of a general purpose, vector processor, right? So one of the is I'm doing vector add, right? That's the work that I really want to do. But to do that, well, I have to fetch and execute instructions that perform address calculation so that I bring that data inside the register file so that later on I can do the vector add on it, right? That's the whole definition of a general purpose processor. You have a register-based ISA that you're working with, right? So as you can see for these workloads that you see, these are the overheads that we are seeing because of these address calculations that we are doing in the general purpose vector processor. We have assumed cache hit here, 100%. The second one is that after you've done the address calculation, you actually need to go to store results from the register file to the memory or from the memory to the register file. That's the red is the overhead. I just don't want to bore you guys with numbers because I think the color itself is like, very, clear what's happening here. The next part of it is that, well, because this is a general purpose processor, you're doing a lot of loop instruction. That's the next overhead that you're paying for performing these non-gem operations. Imagine again, go back. You have optimized the gem unit, and I showed two of my own work that tries to optimize this unit to death. And this is what is, what is going to bottleneck it because you have the interleavings of the gem and non-gem operations, right? So what we did is that, so we actually went after an ISA which doesn't have the register. We completely alienated register part because the source of inefficiency is that you have to perform address calculations and bring the data into the register file so that you can do the operation that you want to, right? But now we want to, and I'm talking about on-chip memory here. I'm not talking about off-chip memory. Like I'm assuming you have massive flash drive because that's prevalent in the, the design of the whatever NPUs, right? But the challenge is that there is a reason we have register files in our architecture because you want to keep your instructions short and you need a namespace. Register file is a namespace. Memory is a namespace. Some buffer that you can, address or index from software that's called the namespace, right? So how do you do this? So, and the way that we did this, we said, okay, we'll have a table in the front end of our microprocessor, right? In such a way that I would configure offset and strides that I need to bring the data. And after that, when I'm doing the execution, I'll just use this information in the table. I'll do the config once and then go after execution of the, the compute instructions that I have to do perform the data, right? And one of the things that did is that this processor that we are designing, right, needs to work across multiple components. And this processor not only gives you non-gem operations, hopefully expands the scope of the acceleration domain that you are working on, because now you are doing SIMD-like operations which with a programmable unit in a repeated fashion that you see very prevalent in other domains than neural network. So what we did is that for us, the addressing mechanism to load these iterative tables is defining a namespace, which gives you flexibility where you're bringing the data in, and then indexing to it, how you're going forward in that. So that's one of the things. So what you see here is, well, what I call Jim Smith had a seminal work called decoupled access execute architecture, and he also kind of introduced the concept of architectural policies and architectural challenges. The idea was that there is a part of the processor that will fetch the data. There's another part of the processor that performs the compute, and you have a FIFO between them. That's called decoupled access execute. What I'm proposing is actually a decoupled access execute. The way that I will use the instruction which performing the configuration for the iterator table to config my table once, and after that, I'll use the information there so that when I'm performing the ALU operations, I'll both index to my scratch pad buffers, get the data, and perform the ALU operation. And I'll show you the the microarchitecture that we have. You have a program counter, you have instruction, you have a fetch unit. These fetch units either are configuring either iterator tables or reading the base addresses and the stripes from the iterator table. The next stage of your pipeline, you're going to perform the address calculation. Now you have all the addresses. I want to do SIMD, but I want to do it with short clock cycles. Usual SIMD architecture, you do multiple lanes in parallel. We actually did it different, right? So what happens is that I'm going to go to the buffer, first buffer. I'm going to fetch the data. This ALU is going to perform the computation. The next element, I'm doing the same computation, so I'm not changing. I'm going to fetch it from here. Next one is going to do. That's why we can achieve high, high clock frequency, because we had to be very careful what clock frequency that There are other units that are performing off-chip memory accesses. You can also read the data from your output buffers. That's your interaction mechanism with the with the gem unit, which is attached to the output buffers. You can potentially write stuff into the input buffer from the standard processor. And now the standard processor is actually managing the whole situation, right? While the gem unit is just pumping the result. And since you have this programmability baked into it, you can actually perform non-idle accesses to your output buffers from the gem unit. Which actually, if you build an NPU, you will realize that if you restrict yourself to the coupled access execute, which has the Python interface, your performance is going to change. And you can't do a lot of the, compile. You need branch prediction. You have to do a lot of large loops, architectural loops, not, I become a paper by drawing those same chips, right? We don't have any of them. And the reason is that a compiler can rearrange the instructions because we can access, data in the gem units buffers, in a kind of a very random access manner. So, well, I showed you a very simple example of vector, right? Like you perform something, but it's not just we're specializing, guys. We're providing programmability. Your ALU operations, we divide it into two categories. You have primitive operations that we're performing, whatever adds up, multiply. Here, higher order operations like sigmoid, tanh, app sign, whatever. Why are you asking me? These are the higher order operations. Solutions because he looked at the benchmarks, he decided these are the right, units. But it's part of it is that, well, you're doing tanh. The reason being for it is that you can do it with a lookup. If you do it regularly, you have to do Taylor expansions, very expensive, right? And if you want to do other things, you have emerging layers, you can have matrices. We give you enough primitives that you can actually implement the newer operations like ALU, softmax, clip, whatever, as a combination of these instructions, and you can use it. Okay? Now, besides what I expressed in terms of the no register file, so far no register file, and not accessing no register file. Also, I showed you we're doing this recoupled access execution, model. But our ISA is actually a block structured loop. ISA. What that means is that you have a block of instructions that is your loop model. You have a TM model, which is the configuring of the processor, and then you just loop over it with the, with the instructions, the compute instructions that you have, which is very fitting. Now let's go back to our previous example. This is the vector add from a general purpose processor. So you're going to run this loop n times Well, you're getting efficiency by dividing the n by the number of, I mean, it was an m, you divided it by the number of the elements in a vector, right? So you're getting a boost there. And when you look at RSA, you have a preamble, which is running first, setting up your iterators, PCs, a bunch of other stuff, and then you just loop into the compute. And that's the only thing that is running in time. And all of us know we have a lot of repetition in the computation of the neural networks that we have. So we actually thought about supporting mixed precision execution in there. This is right now the IC that I'm showing is like how many bits of fixed point you can, integer bits of fixed point you can. Again, you set it up, then you perform your data conversion if you have to. And this becomes important because, like, if you actually want to achieve high accuracy, usually your gem unit runs on a different precision than your, your vector unit or the tandem processor, right? So that's one of the other things. The other part of it is actually you need to synchronize with your gem units or other units that might have, the chip. As I said, you have a block structured ISA. You have the sync start end, which defines the block of the instruction. But there's another important instruction that we have provisioned, and that's when you release the output buffer, right? The output buffer of the gem unit, so that the gem unit can step forward and do the next part of the computation that it needs to do, and you can enable software pipelining, between the tandem processor and the gem unit. So naturally, if you're performing tile-based accesses, when it comes to getting data from the external board, again, you have config, actually you have config and walk instructions that performing inter-tile accesses to the object. And then you have config and walk instructions that perform intra-tile accesses. Because you bring a tile, you're still doing SIMD, level of operations. So this actually comes with an open source compilation stack. Part of it is we're doing some template, code that we can match whatever you're running. And this is already available. As I said, the dimensionality of the vectors that you want is completely configurable, and it can match whatever gem unit that you are designing. So this is part of the Genesis, infrastructure that we are presenting. Well, I have to show you some numbers, right? So otherwise the talk would be incomplete. Well, we are better, but there is an interesting part to it. This is arranged in a temporal fashion, like as we go forward. So this is comparison with another NPU, which is using dedicated units, but it has another open source, as a baseline. And we see we're getting up, around 2.66 speed up. We're getting much higher energy and efficiency, because if you don't have the block inside, you have to go outside. And that's a homogeneous energy. Another important insight is that we're getting better benefits as we move in time. Classical models, yes, they were more matrix multiplication, not these. Now you can actually compare that to a normal vector, processor, like the one that we showed. You're getting 2.6 speed up, you're getting 1.4x energy reduction. The reason that your energy reduction is not that much is that we have actually given an open hand to the general purpose vector processor. We have assumed no overhead for address calculation, 0. And the reason was that one of the reviewers. So, and that doesn't seem like that's realistic, but it's okay, right? Another, assumption that we have made is that both processes are being tied, which is performing on-chip, computation. I think that's reasonable. So because the energy is more dominant when it comes to off-chip transfer of the, the computation. Well, thank you very much for giving me an opportunity to present what research we have done. This was actually a direct result of building accelerator generators while developing their compilers that we have been working on for so many years. This was supported by multiple grants, including the DARPA RTMO, and then I have an NIH project on that. You can access the code, the compiler, all of it is available. Tomorrow, my excellent students who did the work, I'll just get to blab about it. I'm going to present a tutorial in the afternoon. You're very welcome. It runs on FPGAs, even Amazon F1 instances today. I learned that from, Steve Jobs. So today you can actually get it working and the compiler comes and we can do run end to end and it's actually functionally correct. And I challenge you to go find another open source project which can do end-to-end neural execution. With that, I'm happy to take any questions. Thank you very much. Right.
So in that case, the benchmarks which you tried, like softmax or Gelu or any nonlinear operation, what was the length you tried for that? Because and more so, how do they adapt to the current situation where your softmax length is increasing every iteration?
I mean, yes, we matched whatever exists. Like we have a TPU-like architecture that we compared to, right? So we're not limited. The details are in the paper. There is an extensive study on that one. So we didn't choose anything that is in our favor. We chose what was available at the time when we were designing it, and you can expand it. Sure.
But now, the case your length is not fixed. Always keep on increasing by one every iteration, right? So
Sure.
In that case, what does this do? Like, does it expect padding, or it is efficient enough to compute those dynamic length softmax operation?
Well, it can do. We're doing it like either you have a tile that you're bringing and you're performing tile operations. Well, we have that ability. If you're doing individually, then why are you even doing vector operations? Sure, that's not a problem. That's not a problem. You just bring it like tile by tile, perform the computation. The tile size is something that the compiler decides based on the memory bandwidths that you have and based on the, the number of lanes that you physically have, decided your design is going to have. That's a parametric, part of the compilation that's going to be decided. And you do a search space analysis on that and see what is the tile size that's going to match it. Sure, definitely. All right, thank you.
Modular where she works on building the integration infrastructure for AI. Which was done in Monster.
I it to this should be here, I hope.
We can move full screen if you want.
Yeah, it's probably. Where do I click to make it full screen? Okay, thank you. Yes. Okay, so I'm going to talk about very different topics of software systems for AI and Mojo, which is a programming language for AI. So as everybody here knows, software costs of generative AI are through the roof, and it would be really nice if we do something about it. And one of the biggest problem here is the cost of AI infra. It just takes a lot of energy to run Gen AI models. And that energy, if we look under the hood, what is happening there? A part of it is hardware, part of it is software stack, which runs on top of that hardware. So then the obvious question is, what can we do to make the software stack more efficient? And if we look at the software systems, then there are so many different kinds of this. There is no uniform solution because everything is being built ad hoc, right? There is PyTorch, JAX, TensorFlow. There are so many different inference frameworks. Effectively, every hardware company builds its own inference framework because that's the way they can get maximum performance out of their hardware. There are different different serving frameworks. Of course, all of this runs on GPUs and sometimes on CPUs, and then there are accelerators, which everybody is building, and some entities are even deploying. And if we look at the space from the AI developer point of view, there are just so many different things. We program AI systems using Python, C++, CUDA, and that's all a single application, which part of it was written in different languages. Different frameworks have different APIs, and not only APIs, but programming conventions, because it's not enough to know APIs. You also need to know, like, what is a particular idiom that you need to use to make that API work for you. And every tool has its own interface, and somehow AI developers are supposed to learn this. And what it practically means is that because this world is so complex, everything takes longer, right? You cannot just implement a model and deploy the model. You need to make sure that this model runs fast enough. You need to debug it. It all has to be done using some tool. And if you switch to a different hardware, it's a different tools. And so the thesis here is that could we build a unified framework which would allow us to get things working faster, to extend the framework faster? And that was the main motivation why we at Modular created Mojo, so that we could have one programming language for different tasks used at AI. So if, so first of all, what is Mojo? On the right here, you can see the example. It's Mandelbrot kernel written in Mojo, but some things to kind of learn here is Mojo is a member of Python family. We use Python syntax, many Python concepts. It is a superset of Python, but it also allows system level programming. And as you can see here, there are types which you won't find in classical Python. It's incredibly fast because it gives you system level control. We try to make it usable for developers, so it actually has a tool chain. There is syntax. The syntax highlighting, right, is from VS Code.
You can jump to definitions. There is a debugger. It's freely available for download. Parts of it are already open source. We put out the standard library, and we have a growing, vibrant community who works on it. So one way to think of Moja is a Python developer ecosystem plus next generation programming language design. So why do we care? So one of the key features of key innovations of Moja or design principles was to give power to library developers. If you look into what are the ways to build machine learning systems, usually there are two ways. Either you write a library of high performance kernels or you build a compiler. But if you're a compiler developer, and then you look under the hood of what are you doing building that compiler, actually you are writing a lot of things which look like high performance kernels, but instead of written in, well, assembly, in line C, intrinsics, they are written in calls to your favorite intermediate representation builders, because you need to generate that compiler representation, which is the output of the compiler. So what Moja does instead, it uses library approach, and we take it all the way down to the bits inside the language. Again, if you look into how programming languages are built, usually fundamentals are part of the language. For example, types are parts of C++, right? You can define your own type, but then it would be in the library, but integer is part of C++. So in Moja, all the types are defined in libraries. And this gives the Moja developer the power to build the whole stack from bottom up. For example, we all know that languages should support integers, but what about FP4 or bfloat 16? So with Moja, every type has equal rights, and we can build them all together. And what it means for Moja developers is actually incredibly powerful, because it means that you can build compilers as a library effectively in Moja, bottom up, all the way to the top. So let me show you an example of what matrix multiplication in Moja would look like. So this is toy because we don't even do Thailand here, but it runs much faster than naive matrix multiplication loop, because there are some interesting things here. So there are these two things called vectorize and parallelize, which are compile time functions. And what is going to happen is that this program is input to the compiler, of course, but the first pass of execution happens at the compile time. So this is, think C++ templates on steroids with much better type checking and much better tooling. You don't need, if you want to write vectorization, you don't need to write it as a compiler pass. You can write it in the language. Same for parallelization. And so what it allows the programmer is to build their own abstractions ground up. Moja is part of Max. So again, looking at the space is fragmented. I work for Modular. Modular builds modular accelerated execution platform, which includes three components: Moja programming language, Max engine, and Max server. Max is a powerful machine learning framework. It supports PyTorch and TensorFlow, runs on CPUs and GPUs, and it provides extensibility. So I'm going to show an example of how Moja could be used to build extensibility for Max And again, this is a very different level of use for Mojo, just illustrating the premise that we have a single programming language which can be used bottom up to define types, to write high performance kernels, and to provide extensibility for the engine. So we start from looking at the PyTorch model. So this is a simple PyTorch model, right? 3 operations. We can pass it through the torch compile. And what we will see is that the output is 3 operations. And of course, if we want to generate efficient code, these operations must be fused. But this doesn't happen because torch compile doesn't implement fusion for these particular operations yet. And of course, I'm sure that it's very easy to add, but you need to add it for every combination of operations in your machine learning compiler. So, and the whole process of adding custom operations is rather cumbersome, right? You need to write them in C++ code, use specialized macro to add them, build it, and then provide this to Python. And what we get out, of course, because we got 3 operations, a lot of code. So now in Max, we use Mojo. So again, this is pretty similar, right? This could be Python. We write kernel for CumSum in Mojo. So again, this is like this is already pretty unusual because we write the model, right, in the same language as we write kernel, and we do get performance. You cannot do it today with Python. To package the kernel is very easy. It's one line. And then to deploy it, all what we need to do is to specify the path to packaging. And then Max does optimizations, including fusion on custom operations. And the result here is that whole program got compiled into 15 lines of assembly code. Right? Our ReLU is one instruction as it's supposed to be, and multiplication and CumSum is a single FMAD as it's supposed to be. And this is I think this is the key towards unlocking combination of programmability and performance, because we want to program at high level, but we want to get low level performance in hardware. And that's what Mojo allows you to do. And this is difference in the code that we generate for Mojo, for Max with Mojo versus what happens in PyTorch. We actually do generate that tiny snippet of assembly on the left. And the initial incentive for building Mojo actually came from us needing to have a better way to write kernels. And all kernels in Max are written in Mojo, and we do get top performance for that. So another use case illustrating what you can do with Mojo is Max graphs. So of course, every Max can run TensorFlow in PyTorch, but of course, every framework wants to provide its own API. So does Max, and this is a simple example of the APIs that we have. You can define a model, and then you can start building blocks out of this model the way you would do like with any programming language. We have example of this using Max graphs in Mojo in Max open source repository. So just to summarize, we believe that we need to build software which allow people to program in a single programming language and to rapidly innovate. And to do that, we build Moja, and we build Max, which is built on Moja. And with Moja and Max, any researcher or developer can build any part of the AI software stack while staying within a single programming language. So if you are interested, please download Max. It's available on our website. Moja is part of Max. We have Discord channel. Our standard library is an open source. And play with it and let us know what you think. Okay. Any questions? Yeah.
Thank you very much for hardware design, which I really think this is important for different hardware, different companies. So I wonder, does some like the support for the non-GPU type of architecture, like what's the challenges to integrate for the integration of the module? I think that's something that is straightforward.
Okay. So the answer is that conceptually there is support, practically not yet. Try it maybe in 6 months to a year. So to conceptually, yes, because Moja provides the ability to interface with MLIR and LLVM. So any hardware accelerator which has MLIR or LLVM interface can be hooked into Moja. Can be programmed from Moja and can be hooked into Max. Right. So the only thing is that Max, public version of Max, does not yet provide these hooks. Right. And Moja doesn't have, again, publicly full functionality to do it just because we are focusing on other things. But the architecture is there. And yeah. Thank you.
So next speaker is Vinky. Vinky Arjun is a research scientist at Meta, where she's MLP. She's working on building efficient, high performance, and sustainable online systems and alternatives. She received her PhD degree in 2017 in the Department of Computer Science at UIUC.
Hi, everyone. Thanks for coming to my talk. So I'm going to be talking about Chai today, which is a clustering-based attention head pruning method for efficient LLM inference. And I want to start with some motivation behind why should we care about efficiency at all. So in this plot here, we see data center energy growth trends in the last decade. So from 2010 and 18, as a computing industry, we enjoyed almost like a flat data center energy consumption. The usage increased only 6% despite the 6 times capacity increase within the last decade. And this has happened because of efficiency improvements. If we did not work on efficiency improvements, the energy usage would have been like this gray dashed line here. But things have changed within the last couple of years. Data center energy use is projected to double within the next coming few years. And this is based on the upcoming current constructions and upcoming expansion plans.
So data centers currently consume about 3% of the global energy demand, but this is projected to increase to 7% by 2030. And AI is a big part of that demand. And we see that the demand for AI hardware has reached an all-time high. And in the meanwhile, the concerns for carbon footprint of the AI models have been building up as well. And that's why we need efficient AI more than ever. And we need it for both inference and training, which we see both are equally important in terms of resource consumption. So with that motivation, with Chai, we aim to tackle the inference problem, inference efficiency problem, particularly LLM inference. So let's switch gears and dive deep into LLM inference. So in this plot here, we see the inference operator breakdown of across a different family of models, LLMs, text-to-image models, and text-to-video models. And what we see here is the pink part, which is the attention component, is the major bottleneck across the set of models that we are looking at here. And the second columns here shows attention with flash attention. So even after flash attention is applied, you see that the attention is still the major bottleneck across different set of models. And in the case here, in the Chai case here, we are going to be looking at LLMs, and the Llama model here is Llama 2 based on 4K sequence length, but with we don't have Llama 3, but with Llama 3 we have even higher context length of 8K. So I expect that the portion of the pink portion would be even higher with Llama 3. So this shows the importance of attention, and that's what we are going to try to tackle with Chai. So attention, I think, does not need introduction here, but just to make sure we are on the same page. So just a little bit of background of attention. So we have our like QKV matrices here, which has a size dependent on the sequence length. And then you have linear projections, and then the attention score is calculated by QK transpose, softmax of that times V. And the complexity of attention comes from this dot product attention, which is based on the sequence length. And another thing I want to mention here is this happens each times in parallel, and that gives the number of heads, the multi-head attention in a component in attention. And that's what also we will be looking at with Chai here. Just briefly showing this with an example. So during the prefill stage, you have your input sequence. Monday is the here, and then you do your linear projections, get your QKV matrices, and then you multiply QK transposed, takes the softmax of that, and then you get your attention score matrices here. And then you apply that, you multiply that with V, pass through MLP layers, and then you get your next token first. So you have Monday is the first now. So now in the decoding stage, instead of a matrix here, which is a sequence of tokens, you only have first. So you do the same thing essentially, but with a vector now. So you go through the same computation, and now we get the output as day. So Monday is the first day. So now, because you do a vector instead of a matrix multiplication, the decoding part is has less compute density, but is more bottlenecked on memory, as many of the talks in the morning has mentioned as the memory read and writes being the bottlenecks in attention. But with Chai, we are gonna try to prune the Q and K matrices here based on the attention scores calculated here. So, okay, now you have all the background that is needed to understand chai. So what is chai? So chai identifies redundant heads in multi-head attention and clusters them together just by selecting one head from the multi-head attention within the cluster. It does this dynamically during inference in order to reduce compute and storage requirements. So I want to give some motivation and design principles behind chai, or also what makes chai unique compared to many other pruning methods that's out there. So first, we want to try to, our motivation is try to reduce the latency and memory capacity requirements from KV cache. We don't want to just reduce the flops. Second, we want a method that does not require any training or fine-tuning, and just a purely inference-based method. Because training and fine-tuning is hard, even with methods like LoRa and QLoRa, with really large models, they're hard to train. Also with pruning, you won't know the accuracy impact of pruning ahead of time if it's a training time method. So you need to do the full training loop to be able to see the accuracy impact after. So it's better to have a just train without pruning and apply it during the inference time. And we want to also keep the compute dense, which makes it easier to accelerate, so no sparse kernel implementations are required. So I'm going to talk a little bit more about the related work to chai. So this was mentioned also earlier in the morning, but there's a lot of methods that tries to optimize attention, such as sparse attention or approximation methods. Most of the problem with this work is sometimes the sparse methods reduce the flops, but they don't end up reducing the latency. And also many of these work require either training or fine-tuning and cannot be applied directly during inference. But I'm going to talk more in detail about the three work that is closest to chai. The first one is déjà vu. So déjà vu is a recent work that applies pruning to attention heads also dynamically during inference. It does this using training a small MLP layer offline and uses that MLP online during inference. It also prunes attention heads that gives uniform weights across tokens, which seem to apply well for older models like OPT, but doesn't apply for Llama. I'll give more details about that later. The second method is SP10. And this was also mentioned in an earlier talk by Song Han. And this method removes tokens and heads based on importance scores in inference again, and it uses a top K based method for head selection. Finally, there's group query attention. This is not really a direct competitor to chai, but it is a fine-tuning or fine-tuning based method. And this groups the KV values across heads with different grouping factors. All right. So next, I'm gonna give some observations about attention scores that led us to our design of chai. So here we look at the activation scores of OPT and Llama models. So OPT 66 billion model here has 72 heads and Llama has 32 heads. And each row here shows a head, shows one head. And on the x-axis, you have your token IDs. So first thing to notice is OPT and Llama seem to have different patterns. Both have shows lots of sparsity, but with different patterns. With OPT, you see there are several heads which gives uniform attention scores. But with Llama, you see the high scores for the first token, like also called attention sink. But there are also no heads with uniform attention scores across tokens. And the prior work based on OPT, which seems to use this like uniformity, exploiting these uniformity pattern, which did not apply to llama. So we wanted to build a method which would apply to both of these sparsity patterns. So now we wanted to take a look at the correlations between heads. So these plots here shows the correlation scores across different heads in llama this time. And what we see here is that some of the some of the layers have high really high correlations, so you could almost like cluster these heads, and this correlation seemed to have increased in the later layers of the model, as you can see here. In the earlier models, layer 1, there doesn't seem to be like bigger clusters, but as you move towards later, the layer 30 here, you see a big chunk of heads here that have very high correlation. So this observation shows the opportunity, implies that the opportunity that we should be able to cluster these heads and reuse the scores from reuse the scores in the cluster. So that's why we had run a k-means clustering across activations of different heads, and we look, and then the plot here shows the k-means clustering error, and the little dots here shows kind of like the optimal number of clusters we observe. And what we observe is these like number of clusters with similar output remains almost constant across requests. So you change the requests, but the optimal number of clusters does not seem to be changing. So implications of this is that we should be able to determine the number of clusters offline statically, and should be able to use it per model, and you should be able to use it later during inference. So another observation we have, now that we have looked at the number of clusters, but for each request, we also need to look at the membership of heads to the cluster. So the plot here shows how the average membership, cluster membership changes across different tokens over time. And what we observe is that after processing a couple tokens in your prompt, the cluster membership does not change significantly. So the implication of this is basically, if we could process a few tokens during inference, and then we can keep the cluster membership the same during the rest of the decoding stage. Okay, the final observation. We also look at the cluster distribution. So how many, So how many heads are there in each cluster? In this case, we have 4 total number of clusters. And what we find is that most of the heads belong to a single cluster. And there's like a smaller tail. So this implies that we should be able to have a significant reduction. If we use only one head from the cluster, we should be able to save significant amount of compute. So based on these observations, we have designed Chai. So broadly, here's your multi-head attention, and here's your clustered head attention, where we have grouped key and query vectors based on the clustering algorithm, which I will mention now. So in step 1, we need to do a offline cluster identification. Is for each new model you have, we run k-means. So we collect activation scores on a couple samples of your pre-trained data sets, and then we do an elbow plot analysis to find the optimal number of clusters from k-means. And in this case, for example, here in your multi-head attention, you have 5 heads here, and you determine the optimal number of clusters is 3. And then you need to do this per layer. For second layer, it is 2, and then the other layer, you have only 1 number of clusters in this particular case. So after this offline stage of when you determine number of clusters, during the inference stage, we need to, per request, we need to determine the membership of heads to each cluster. And we do this again, like I mentioned earlier, from the observation, we ran only a few tokens and collect the activation scores after running a couple tokens from your prompts. And then in this example here, for example, you have 5 heads again, and then in your first cluster, head 1, 3, 5 belongs to your first cluster, and head 4 belongs to second, and head 2 belongs to the third one. And then you do this for each layer. We also built a static version of Chai to see how important to do this dynamically per request. And the static version of Chai, we determine the cluster membership of heads to the clusters offline as well, not per request. That's the only difference. So, okay, let's talk about the results now. What does Chai gives us? We will first look at the computational efficiency. So in terms of memory capacity, we find that Chai is able to reduce the memory capacity by about 20%. This is coming from the KV cache reduction. And we apply it to Llama 7 billion here. And in terms of time to first token, that is your latency, we observe up to 1.7 times speed up for the sequence length of 2K here. The benefits improve with higher sequence length because in the first few tokens, since we need to do clustering, there's a little bit of overhead, but you don't need to do that for after a few tokens. So the overhead gets amortized over time. And in terms of time to next token, Chai gives about 5 times speed up for a sequence length of 2K. So now let's look at accuracy. So we compare accuracy with the baseline methods that I mentioned earlier, déjà vu, sparse attention, and static version of Chai. So the first row here shows our baseline multi-head attention accuracy score, and the other rows how much deviation, accuracy degradation or deviation each model shows compared to the baseline multi-head attention. So first we observe that the related methods, déjà vu and sparse attention, both performs very poorly and reduces the accuracy by like 10% or 20% in some cases. In compared to that, Chai only causes a maximum of 3% impact on accuracy, and we evaluate across a set of evaluation tasks commonly used for large language models here. And in terms of the Llama 32 billion model, which is more sparse, the accuracy impact is much lower, and in some tasks there's like no impact at all. We also show the static accuracy of Chai static here, which is slightly higher, but still better than the other methods like déjà vu and sparse attention. Here we look at the accuracy and flop trade-off, and Chai seems to show the best trade-off between flops and accuracy, and sits on basically the Pareto optimal curve here. Okay, now I'm gonna talk about some additional experiments and ablations we did with Chai, and which one of this is group query attention. So group query attention, as I mentioned earlier, is a training-based method, and which does the clustering, not Qs and Ks, but it clusters Ks and V values during training. But what we found is we could apply Chai on top of group query attention and still get benefits. So here we apply smaller Llama models does not use group query attention, but the larger models, 70 billion model here, uses group query attention. And it uses a grouping factor of 8, means 8 queries are mapped to a single K vector. But we could apply Chai on top of group query attention, and we find that we could reduce the K vector further by 1.8 times and Q vectors by 3.7 times, with very negligible accuracy here for these large models. We also tried Chai with quantization. It is important to be able to stack these efficiency methods on top of each other. If they don't work together, then the benefits will not add up. So that's why we wanted to try post-quantization method like GPT-Q. We applied that to we take a quantized GPT-Q version of Llama and apply Chai on top of that. And it's a 4-bit quantized version. And we also see the same insights we applied for non-quantized version of Chai applies to the quantized version as well. And we see negligible accuracy. Finally, another ablation study we did with Chai was, could we prune whole QKV and reuse the whole head instead of just QK values? But that showed actually quite a significant loss in accuracy. So it seems like removing the whole head is not really possible without getting accuracy, significant accuracy impact. Okay, with that, I will conclude my talk with some